All right, it's been a very, very long time. I think last time I recorded was like a week ago, and I haven't been able to work on the robot because of work. But today I was like, no, we actually need to get this done, get this over with. And so, yeah, I think where we left off, I finally gave up on trying to make the robot walk, just hard coding it based on visuals, and I said we were going to do inverse kinematics. And yeah, that was the last bit. And actually, after that, someone reached out from the audience and said, "Oh, I'm also building a quadruped robot." I actually went to his house and showed him the robot. I actually broke the leg while at his house, but it was, first of all, super interesting to see that other people are building robots, and I really love that people reach out to be like, "Hey, I'm building one too." Oh, maybe I'll put a picture of his here. I think he hasn't posted online about it yet. It's kind of like add-on, but we have similar designs but are doing things very different. And also he has an AMS for his bamboo, so he can print in multiple colors, which looks very clean. I almost regret going like the very colorful, like super bright blue route, but we have a ton of super bright filaments, so we're gonna stick to it. His was all white and black and looked very clean. I think there is value in making something that looks clean and professional. You know, if something looks good, well, people often, I don't know if you can hear me, my screen went dark. If something looks good, people often assume that it works great as well. So that's true. Anyways, the other thing that was different is I'm using an Arduino board as my microcontroller, and I understand that eventually I need to move out of here if I'm going to host an ML model. And I've said, you know, I've talked about Raspberry Pi 5, the AI hat, and so on, but this guy already had Raspberry Pi. He had a Raspberry Pi. He didn't have the 5, but you know, I took a look at Raspberry Pi. You know, runs on Python. Seems like very tempting. And also Raspberry Pi has a few boards. Small board has a few boards. Let's see, I'm trying to remember the Pico board, for example. Very small board, very capable board, $4. But the most interesting board I saw was the Raspberry Pi Servo 2040, I think. Was it 2040 from Pi Moroni? So this board in the middle here, which could, you know, it's basically it can handle 18 channels of PWM servos, which is we only need 12. And it could, in theory, be able to power them. That's not so clear, but you know, basically one board where everything plugs into. You know, it would simplify our wiring a lot. Yeah, he also had his servos run on UART, and so what that means is that each servo didn't need to be wired to the board for power. You can basically chain the servos, kind of like so here, and so your wiring ends up being much cleaner because you basically only need 3 wires per limb instead of right now we have 9 wires per limb, which is a lot. So that's clean. His servos were also, you know, much more lightweight. Our AliExpress servos probably a bit too much. His servos also had full 360 degrees of motion. You know, ours are capped to 180, so it's very important to initialize them correctly. He didn't have that problem. So really, you know, there's a lot of room for improvement here. That was exciting. The servos I'm using do move faster. So I think eventually we might be able to even jump on this robot, but we'll see about that. You know, my servos also draw a lot more current, so my battery is much bigger, much bulkier, and seems to draw energy like much faster. But anyways, the other thing was, oh, also by the way, check out this drone, the AOS HS5, which is like basically a high speed. I think it's open source. It's an open source project for a high speed. Damn, my face looks so dark. High speed project for kind of like a open source project for like a racing drone, which is very interesting. I think Red Bull, I don't know if this is the same one, but Red Bull had a video of their car. It was like Red Bull Formula One, versus drone. Yeah, see, and it looks very similar to that. So maybe it's inspired on that. It doesn't quite look the same. But yeah, that drone was super fast. So that was interesting. And I'm gonna save these maybe later. I do have a drone. It's a regular quadcopter. I'm not gonna build another drone until I actually learn to fly the other drone. And then I was looking at this robot, the Diablo. I was just thinking it's just a nice and fun shape factor made for a future robot iteration. I don't see us moving away from 4 limbs for the foreseeable future, but this was very fun. And it looks very rugged and super, looks fast and looks like it can go anywhere off-road. Anyways, kinematic equations. Now, unfortunately, I did kind of cheat and I did start to do some math on my own. It was like a super slow process, so I didn't record it, and it was like me basically doing work to try to figure out kinematic equations. Kind of looks like these. It's a lot of tricks. I haven't finished yet. I have the kinematic equations working, but I haven't finished them. I haven't turned it into code yet, and I haven't uploaded it to the robot. So I was hoping to do this today, so over the next 4 hours or so, and eventually I think let me walk you through how they figure this out. But in essence, I was trying to find, because inverse kinematics is something they teach in university, in school, engineering schools. It's well understood. So I was trying to find an example that was exactly the same as the leg we have here, but I couldn't find one. So I couldn't find one. I found a couple that were close enough, and I also found people on Reddit asking for it, because there's a few open source projects that use the same leg as us, but kind of no one has the inverse kinematics for that. And so I might do a video of that, but basically let me explain. So first of all, our leg is a board from the Dingo quadruped project, which is in turn actually heavily borrowed from the Stanford Popper. And if you go on Dingo quadruped under kinematics.py folder, you can see their leg explicit inverse kinematics. The name of this function is because you need to solve inverse kinematics on a leg level to be able to move the feet according to your servo angles. But you also need to do the same thing at a body level for yaw, so the body can rotate, can look up and down, and so on. So this is for the leg. And then you can do here. There's a lot of variable control, variable stating, and they do a good job here with the comments. But it kind of boils down to these here. So it's kind of like the math behind it. Now, I didn't want to just copy and paste these, right? I wanted to understand where it came from. Because in the future, if we make any change, we need to be able to understand how that's going to impact our inverse kinematics. I also went and looked at the Stanford kinematics.py. First of all, you can tell Dingo was very inspired by Stanford. Even their files names are the same. Their documentation parameters look the same. The Stanford code is a little cleaner, but even I think their function name, it's literally the same, right? So I think Dingo got a lot of credit, but actually I think these Stanford guys put in a lot of work. And here you go, like these are the trick equations basically. And of course you could copy paste these, but it's unclear what's phi, what's beta. I mean, maybe if you read the comments, but I think there's value in doing it from scratch. So I went and said okay, I want to do this from scratch, and of course YouTube was the first stop. I think YouTube is cool. This is a video we were watching last time, I think. These are all old videos we were watching last time. Yeah, I don't think Spot is good. Like Spot was interesting for inspiration, but of what like a crawl or a trot could look like, but like Spot actuators just move so much faster. Anyways, looking at the Stanford Popper, I also found these Stanford Popper website. They actually had a whole lab on inverse kinematics, and here there's videos you can you can replay of lectures where they walk you through what's inverse kinematics. Unfortunately, the examples they use are for robot arms and not for a leg with like two four bar linkages. So this, I mean, this is kind of like interesting for the math aspect, but it's not what we needed. Yeah, so this is cool, but on its own, not what we needed. Then there was this video here. This is part 2. So in part 2, this is where they explain the body level inverse kinematics. I haven't done any of that yet. Let's get it walking first, and then we can do more fancy movements. Now this was, I believe this was the yeah, this is the video that I think is the best. Actually, what else do we have here? What is this? Yeah, this video was also good, but let me explain, right? So, so this video here, you can look it up here. You know what? I'll put it in our document here, part 8. Is this video part weight distribution? Rows on 3 legs. Inverse kinematics. Useful videos. I'll put this here. Anyways, this video is great. First of all, it explains why we want to do inverse kinematics, right? We want to be able to command XYZ coordinates, and you know, we have to command angle, or PWM, or aka basically translated to angles or servos. And so translating those servo angles to XYZ coordinates is actually, you know, involves math, and that's what doing inverse kinematics is. We want to get to a point where we can command XYZ coordinates, and the robot will figure out the angles instead of we having to figure out which angle we need for these XYZ coordinates. It's much easier for us to provide XYZ coordinates. You know, you could basically draw a square in XYZ. That's very easy. Figuring out what angles you need, not so easy. So it gives you the motivation. A refresher here on trig. You know, Pythagoras. You need your sine, your cosine law of sines, cosine law, and so on. And then you'll need to fix to solve this in two planes. So the YZ and the XY. And the math is super straightforward, really, super straightforward. And you know, you get to a point where you can basically, let me see here, I don't fully recall. By the way, this robot here is called Spot Micro. I think it's also open source and looks very clean. You get to a point where you have these equations that can help you solve the angles you're interested in this case, theta here, phi here, and omega here, right? So we have an omega, a phi, and a theta equation, which we can just kind of like do math and solve. And that's all good, right? Except, well, that's all good because one of our servos is indeed omega, right? That's the shoulder joint servo. In a robot, the servo that rotates the leg like this, that's omega. The servo that rotates the leg like this, that's theta. But the servo that rotates the leg like this, because this angle in here would be phi, like the same as the purple here. That servo is actually not here, right? It's connected. It's like first it goes through this 4-bar linkage, then onto this other 4-bar linkage, and only here it's a servo. And so the angle phi here is not the same angle as here, and it's actually not linear. So if you increase this angle by 10 degrees, it doesn't mean this servo angle will increase by 10 degrees also. So you need to figure out that, and to figure that out, that's not inverse kinematics. That's actually, you need an analytical solution for a 4-bar mechanism. So this video was good. You know, it's 4-bar linkage. It's basically a lot of trig again, and what you're trying to do is to figure out a set of equations that correlate the movement of the knee here, the knee here, onto the movement of this servo crank here. And that could sound, maybe, I don't know if you know trig or not, it could sound hard. I would say it isn't hard. It is kind of tedious to do by hand, so I did it all by hand, and yeah. So that's basically what I did, and you know, I might do a future video again just doing this manually, but let me see. So the first step after you get the equations, the first thing I did was put them in Excel, right, on a spreadsheet. So this says single 4-bar linkage equations, right? So I'm solving the equations of a 4-bar, you know, I have theta 2, and I want to get theta 4. Now that doesn't make a lot of sense, but let me show you. So I find that it helps a lot instead of just solving these things mathematically on paper. What actually helps a lot is just going on Onshape or any other CAD program, do a sketch and define the angles. And so that's what I have here. That's the wrong orientation. And that's what I have here. Now, this might look like an abstract, but this is actually the same leg we have on a robot, right? So this is the leg, the bottom of the leg. This is the leg upper. This here represents that section of the leg, like basically this tranche here that goes beyond the knee joint, but it's still part of the leg. This element here is this 4-bar element. This element here represents this crank here, the distance between this and the pivot point. This element here, this element here represents the distance between here and the pivot point. This element here represents this 4-bar element linkage. And then this element here is a servo horn. So in this sketch, we can basically move things. We can, well, first of all, you know, provide an X and a Y. So this is our X and Y coordinates. Actually, I don't know if that's exactly the same axis that we've defined, but this is how I would define X. And so you can see here, like, you know, when the leg, when the feet is like 39.8 millimeters away from the center of rotation, which is the middle of the hip, you know, you can find the angles here. And so that's basically what our equation here predicts, right? So we have the input X 39.8, same as here, and then Y is going to be 170. And for those inputs, you know, the theta in degrees, which is the hip, should be 67 degrees, 67.15, right? So we go to the hip here, which we said was here, and we look for, let's see which, here, 67.153, which is precisely, you know, we have more decimals here, but it's precisely correct. And then it works out through the linkage here, and eventually we get to, I think theta 2. Theta 2 is the horn, 172 degrees. So this is the horn here, and it's like 172 degrees. Now, 172 degrees from, so that works out, right? The math works out and we validate it on CAD, so that's great, right? So we finally figure out inverse kinematics, at least on paper, at least the math, which is awesome. Again, not as hard as I thought it would be, but I did have to brush up on, you know, I did have to watch a couple videos on inverse kinematics, and I had to recall all, you know, the 4-bar analytical solutions and some trick, you know, a lot of cosines, a lot of sines. Very basic stuff. Anyways, now that we have these and our spreadsheet here that validates it, we need to turn these into code. And the code is basically all the equations in this spreadsheet here. You can see all of the cells here have an equation, and they all feed from each other. We need to translate that into code, which I don't know if it will be easy or hard, but yeah, translate into code. And yeah, that's what we're doing today. So let's open VS Code. So, oh, perfect, already there. By the way, the other thing that has been distracting today was like the US elections. Today is Wednesday, day after the US elections. Trump was declared the US president. And I don't vote. I do live in the US. I do not vote. I'm not a citizen. I cannot vote. And but it does, regardless, you know, you recognize that this is a historic moment, and so I think it's important to stop for a second and you know, just take it all in, because it's probably history in the making to some degree. Anyways, I'm gonna start a new folder here. I'm gonna call this IQ leg, single leg. I'm gonna work on gonna work on Python here for a sec. Yeah, let me, just checking that the extension is up to date. All right. Yeah, so what we want is to, go from X, Y, Z coordinates and solve for the servo angles. We will begin with the rear right leg. Okay, and what else? Okay, so I want to redefine I want to change the way the angles are defined right now. So right now we said this was X, this was Y. So vertical, at least in automotive, vertical is always set. And Y is actually transverse, bilateral, side to side. X is front and back. So I'm gonna define my angles here. X axis is front, back. Y axis is left, right. Z axis is top, bottom. Just always important so we are all on the same page. Okay, cool. All right. And like I said, okay, and we basically are gonna use this spreadsheet, gonna go from left to right. We also have some constant values here. So everywhere it's like L1, L2, L3, L4, those are lengths of linkages. So lengths of linkages are lengths of parts of our body that will not change, right? The linkages on our 4 bars, those are fixed, are not going to change. So we could define those as constants. You know, I have the values, the units here. Servo horn, 4-bar knee. So just gotta name these in a way that it makes sense. What's A, E, and F? I guess it's the same thing. It's these are okay. Okay, input. All right, so I guess first we're gonna find our inputs here. And so I'm gonna start coloring things that we have already passed onto code. Right, so yeah, sorry if I look like a total noob doing this. Literally first time doing this. Input X, input Y, input Z. Also, this is probably like the first time I write code in millimeters. I write code for myself instead of having the AI do it. Millimeters, 170 in millimeters. Okay, so those are our inputs. So defining our inputs. Okay, and defining our constants. Right. So okay. So on the X set plane, D. Actually, okay. Like I said, I did this like last week. I've forgotten. And I have been busy with work, becoming an electrical engineering expert. So, okay. So I mean, I can probably just show you on the YouTube video here. That's sorry. Yeah. So D is what it's in here. D is basically this distance here. Does that make sense? Yeah. Yeah, D is the length of the leg. All right, so D, and we do math for D. It's Pythagoras. But anyways, let's define our constants first. We have a lot of, like the key here is to make things clean. Shoulder to food. I think I am mispronouncing food. I feel like I'm saying food as in eat food. Like upper. But no, I mean food as in like the thing you use for walking. Also, the length of the leg lower was interesting because it's like, which point do you calculate it from? Because we have a curvature, right? And which point in that curvature are you making contact with? Was interesting. I just chose the exact point where it's making contact. You know, since it's a circle, you draw a parallel, perfectly vertical line and choose that point. But I think there's arguments that you could have chosen a different point. All right, I think that's enough. All right, to calculate D. So variable D, is that how we're gonna find it? You gotta import math here, the math library to do math in Python. So square root of input x, wait, no chance you got that right. No, it's input y and input z. Square root of minus, I think C4, what's C4? A shoulder to food square. Okay. All right, so let's take a moment here and calculate let's calculate what our D is. 170 is, and that should match our yeah, it does. Okay, so option J. No, what is this? Yeah, no, oops. And there's a way to get the AI to change a single line. Let's see. Inline edit. Option O. Let's see. Option O. You should say variable D is followed by the value of var D. I prefer the AI to do the formatting stuff. All right, so now when we print this, barrel D is, and that's just important because, you know, we can keep print statements along the way. Anyways, I'm gonna name these. You gotta name this stuff. So this is gonna be so in this, if that was Y set, this should be Y. Oh, it's still Y set. It's still Y set. Y set plane, right? All right, cool. Omega, which is that angle, cheeky angle we're talking about. Omega also very easy. So for omega, so C26. I think there's a way to name your variables. So it's instead of C26, there's names. So C26 is input set, which we changed to Y, right? So, input Y divided by input set with the a tan of d26, which is d, we just bar d, and then c4, which is shoulder to food. And I think we can basically jump to math here. Let me ask the AI what's wrong. How can I make bar omega use the math lib? My screen feels a little small today. Yeah, basically whatever it said, you just click Thunderbolt, it implements it. It's a little slow today. This is of course the double VS Code extension that I use. Print variable omega. This should be obvious. I'm trying to see if autocomplete will complete it. It's kind of annoying. Anyways, variable min is 1.57, which I think matches. Yeah, exactly. I'm gonna add units here. It's just these are radians. Yeah. Cool. We move on. We also have omega in degrees, which is it's completely unnecessary, but we cannot have degrees just for humans to comprehend better. So degrees is radians times 180 divided by pi. So basically that, and so we can just like print this, should be 90 degrees, perfect. 90.0000001. I don't know why, but cool. Cool. I mean, by the way, this is like the first time we're coding on videos, so is coding boring to you guys? I don't know. Let me know. I also feel like since I started to try harder on the thumbnails, I've lost some views. Next set. Okay, next plane, the x set plane IQ, right? So it says xy, but it's x set. The heck is g? Well, g is this distance between the hip and the foot on a straight line. That is probably just a Pythagoras of d and x, to be honest, right? You can kind of tell. You can just, you know, I haven't even seen it. Oh, actually, it's right here. Sorry, I swear I didn't see it though. It's obvious, right? Okay, so bar g, right? Bar g. Yeah, the square root of d and x equals math square root of bar d plus input x, right? And then you can do print, and it's like, well, variable g is this and that, and boom, variable d is 174.6 basically. 174.6. Boom, perfect. You know, just checking along here. Obviously, once the math works, all you have to do is to not mess up, turn it into code. And then here, bar phi. My god. Okay, this one's a little more complicated. So G26 is G. C5 is like upper. C6 is like lower. And again, C5 is like upper. And then we can ask the AI to make these use the math lab. Should do it. Pretty easy, nice. Okay, cool. And then we can just print variable phi. Oh my god, variable phi. I'm using an Apple keyboard. What do you guys use? Variable phi is 1.34. Yep, perfect. And then we can do variable phi in degrees. Variable phi is the knee angle. Oops. Variable phi index. Variable phi 180 math pi. Something like that. Yeah, should do it. Yeah, 79. Does that sound right to you? It is correct. Good job. And now we do theta, so bar theta. We're gonna run out of variable names. That's one of the concerns. It's gonna have to learn the Greek alphabet. Let's see what else they have here. Greek alphabet. Just a lot of variables here to be used. All right, we'll go to like the mu and the lambdas and the news. We won't run out of letters, guys. It's fine. It's fine. All right, theta. Theta. Or theta is this. All right, so A26. A26 is input X. Input X, and then D26 is D, variable D. And then C6 is leg lower. And then H26 is phi, variable phi. And then G26 is G, variable G. And so something like this should work. Make this use the math lab. I should just learn the it just, I mean, it's kind of like faster for I like when it auto completes correctly. All right, so variable theta is 1.17, right? Correct. Good job. High fives all around. Actually, can it? Let's see if it can predict this line. Yeah, it can. Smart. 67.15 degrees. Oh, perfect. All right, we need to comment here that this is a servo input. This is the input for the hip servo. In theory. We do need to make sure we're measuring from the same angle, the same plane as the servos measure. And that's completely dependent on how we initialize the servo. So, and also it depends on like if it's on the left side, on the right side. So some big brain math has to occur there. But that's what we do here. We only do big brain math. All right, and that is basically all of the inverse kinematic stuff. Now, the next thing we have to do here is to translate phi onto an angle for the knee servo horn. Gotta go through 2 4 bars, right? So far we've solved for the angle of this servo here that moves this guy. Now we need to solve for the angle of this guy here, which actually moves this horn here, which moves these, which moves these, which moves these, which eventually moves these, right? So we're gonna like work through analyticals of that, or I have already worked through analyticals of that. We're just gonna code it. The other thing is like, there's probably a lot of simplification that can be done in the code. Of course, I think this is just, I'm not 100% on this, but I imagine every time you do a calculation, it takes some CPU power, and the way it works on C, on Arduino, it's basically, it won't do the next one until, well, it cannot do the next one until it that's the previous calculation. And so it kind of creates a computational bottleneck because, you know, calculate these, wait, calculate that, you know, and it sounds like it's not a big deal, but we're doing it a lot. So it might turn into a big deal. Yeah. I'm going to grab some coffee. BRB. Actually, no. We still have too much coffee. All right. All right. So let's keep on. 4-bar knee. 4-bar knee. 4-bar servo knee horn. Okay. So we have 2 4-bars here, right? So the first 4-bar linkage knee, and then we have 4-bar linkage servo horn. So those are 2 groups. And here we have a y and x variable. These are not input. These are not the same x, y's as the input for the inverse kinematics. These actually refer to x and y here. Basically, the distance between the pivot points of the 2 outermost elements of the 4-bar, which depending on which 4-bar linkage we're talking about, it could be either constant or a trig equation. So for example, on the servo knee horn, there are constants, right? But here there are trig equations, and the reason that is because, you know, basically this point and this point are kind of like are fixed with respect to each other, but this point and this point are not fixed with respect to each other, because this whole leg comes up, and so suddenly the x and y distance between these two change. The overall distance doesn't change, but in x and y coordinates it will change, right? So you can imagine if this leg was completely horizontal, the y value would be 0, and the x value would not. It would be 130. And similar, if it was vertical, the x value would be 0, and the y value would be 130. So that's why it's a trig equation. It's honestly not a big deal. We just need to name these appropriately. So link knee, link servo, something like this. X. Oh, sorry. Y. Actually, we might need to redefine the angles here. No, I guess it's correct. It's correct. Cos. So is that the cosine? Is that really the cosine? Just want to make sure x and y are consistent with the x and y on everywhere else, and I think it is the case, because like I imagine I already thought of these, and if I didn't, what's wrong with me? Servo. Can't find it. X. Oh yeah. Yeah, that's correct. J26 is, of course. What is J26? J26 is the theta, the hip. Yeah. Yes. Yeah. So leg upper. So it's like leg upper times math cos, right? Something like that, of theta bar theta, something like that. I think that's it. Print link knee y. Let's see. 50.47. Yeah. And then the other one is the same thing but just a sign. So yeah, basically that. I can change this here, change these here. Let's validate 119. Perfect. All right. So we have that. Actually, I should really put like an arrow here or something. Then shown. All right. Too much space here. Import math. Okay. Instructions. Oh, that doesn't work. Is it like this? Yeah. All right. Moving on. Theta equals. Man, this is just scrolling is the most annoying part. M6, L6, M6. Theta. So now we have link ni theta equals. It's the math A10 off. By the way, A10 is just inverse 10 of link ni y over link ni x, and then we can print these, and it's like cool. I mean, I'm not even gonna validate. I'm pretty sure that's correct, and then we can do the next same thing in degrees, and then we can do alpha. So link ni alpha pi minus h26. It's like math.pi. Actually, math.pi minus var pi. I think that's correct. Okay, let's run this. Okay, so we have 0.3, 2.4, yeah, 22.8, yes, and 1.76. So all this stuff is correct. I mean, we'll throw degrees in there too. I don't think it matters. Alpha is just an angle we don't care about. We just need it to calculate another angle at the end. I'm working in Python because I'm most comfortable in Python, and also eventually I'm pretty sure we're gonna switch to a Raspberry Pi. I would order the Pis right away, but next week I'm gonna be traveling, so I can't work on this anyways. Like I said, I just want to get it to work first. I kind of like I set this system in mind where like I achieve something, I reward myself with something, right? I achieve walking, I reward myself with better microcontroller. And what else was I gonna say? And oh yeah, and I can just ask the AI to turn this into an .ino, like or turn into C for Python. So it wouldn't be a big deal. Okay, next we move on to L here, and L is it's an imaginary length between D here, this point here, basically this line here. That's what L is. It's not defined here, but I think if you just wait longer in the video, they'll define it, or I define it that way. Pretty sure that's what L is. Let me check my notes. Yep, yeah, for sure. So L is an imaginary length we don't care about, doesn't exist, but it's important for calculating more things downstream. So link ni L equals these, and then we throw this in here. Nope, not that. We want the equation. C9. All right, so we're missing some inputs here. These inputs here. Sorry, we're missing some constants, not inputs. Take these constants from here. So let's define those real quick. They're just constants. It's really like just thinking about how to keep the naming in a way that, you know, it's intuitive for the future. So I'm gonna stick with link ni L1, link ni L2. I think these are all constants. Yeah, link ni L3. L3. And if you're wondering where these constants came from, I basically just measure them on CAD. It's constants from the model. They're all constants, they do not change. Now, as usual, you should specify the units of your constants. You can see this one here might lead to some truncation error. We only have 5 decimals. All right, so now we have our constants here, which we need here. So C9 really is, C9 is the first constant L1, right? So I think it's link L1. C12 is L4. Link L4. C9, it's L1 again. C12 is L4. We need to add a math here. Square root math here. Okay, P26, I guess. P20, what is variable P26? P26 is alpha. So link the alpha. I don't understand. Oh, yes. And this should be, well, I mean, let's print it, but it should be 141.76 millimeters, which is exactly this. And then we go beta, lambda, theta 2. Theta 2 is the angle we're looking for here. It's not the servo angle, it's the crank angle. And from that crank angle, we can get started on the next 4 bar. And this will, I don't know, if none of this is making sense, I will make another a tutorial on how I derived all of this stuff. Just, I don't know, it's like, I feel like some people might find that useful. It is kind of very niche, might be a little boring, but someone's got to do it, guys. All right, so new variable here, link me beta. So math, and then we have a C12. C12 is L4. Link me L4. Math sine P26. We said that was alpha. And R26. Never heard of that. It's probably something we just calculated. It's L. Link me L. Yeah, okay, cool. Well, okay, so print beta 0.259. Perfect. We move on to lambda. Got the wrong thing here. See, now I'm out of coffee. Link me lambda equal equals here. C11, it's probably going to be L3. So link me L3. C10, you know, C10 is going to be L2. Link me L2. R26, I think we said this was L. Link me L. And then C10, I feel like we just had that. L2, link me L2, and R26, was that L? It was L, right? Yeah, L. Just want to triple check. Link me L. So far we've gotten nothing wrong, which is honestly kind of surprising. 1.14, yes. Okay, and finally we move on to theta. Link me theta 2. The theta 2, the number 2, just comes from notation, really, because we don't have a theta 1 defined anywhere. So So S26 is beta. T26 is lambda. So link ni lambda, and N26 would be theta. Never mind, I lied. We do have a theta one. Link ni. Sorry, I totally forgot about you, theta one. And then we can print this angle, and we should print this in degrees as well. So 1 rad or 57 degrees. 1 rad or 57.82. Yep. Cool. All right, and on to the last bit here. Honestly, this is going pretty good, pretty fast. I'm gonna get a cup of coffee. I'll be back. All right. Where were we? Onto the last linkage here. So first things we're gonna do is we're gonna define our constants here. Constants here. All right. So same as before. I think we call these the link servo. So link servo L1. 2, 3, 4, 35 in millimeters, and 37.6 in millimeters, and 42.9 millimeters, 35.2272 in millimeters. Cool. All right, and so now we can get started here. Let's see. First thing, we have x and y. Again, not the same as input x and y. These are constants actually. So on the previous one, they were not constants. This time around, they will be constants. We have servo y. And you can say like, oh, if there's constants, why not put it with the constants? We could. No reason why not to. All right, so first is theta, which is y over x. A10 y over x. So link servo theta equals math A10 of link servo. Oh, yeah, that. Okay, and then we can just calculate these. This one's pretty straightforward. 0.065. Yeah, I mean, I had it in degrees too. Honestly, we don't need that, but sure, put it there. Won't even print it. And then link servo alpha. And I'll put it here. Math pi y26. Y26 is theta. Theta u26 is theta 2. Link ni theta 2. We have a constant here. I'm not entirely sure what that constant so far. Let me figure out what this constant is, right? So I'm just looking at my manual notes here. That doesn't make sense. Alpha. So alpha is theta 2. Yeah, I'm a bit confused, I guess, here. So link alpha equals theta 2 plus pi. Oh. It's unclear to me what these constants come, where does that come from? Little typo there. So alpha is 54 degrees. Let's check here. So alpha should be here. This is 54 degrees. So we're saying alpha equals link servo theta, which is basically this angle here. This is link servo theta, 34.8. Pretty sure. Theta, yeah. Okay. Plus pi, which is 180 degrees. Okay. Minus this angle. Oh, I see. This angle. This angle is this. No, this angle here. So it's a constant. So I'm gonna put it here. So crank angle in degrees. Yeah. So in case if that's not clear. Crank angle is the angle between this point here, the middle of the hip, and this, and the angle between these and these. This is 102 degrees. And I wrote it as a constant there for some reason. All right. We have another L. Remember, L is an imaginary thing, but we need it for calculations. So link servo L equals math square root C18 link servo L4, I think. Yes. C15 link servo L1 C18 L4. Okay, L4 and 15 again. That's law of sines, I think. Sorry, law of cosines. Link servo L4. AA26 is alpha. Link servo alpha. And then add math here. And then we can print it. That's L. And then we calculate beta and lambda. Link servo beta. Link servo lambda. And link servo theta 2, which is gonna be the angle of that we actually care about. The angle that goes into our servo PWM. AA26 alpha. Now I do realize how convoluted all of this code looks. As in, like, if you wanted to troubleshoot any of these, yeah, it might be painful. And we could probably merge a lot of these equations into single equations. C16. But then if something's wrong, if we want to change something, I don't know. Okay. Man, I always forget what AC26 is. AC26 is L. made a typo here. Link servo. I made a lot of typos here. Okay, and then last but not least, this should be a simple arithmetic. Oh, sorry. This should be a simple arithmetic equation where y26 equals theta, right? So link servo theta, AD26 equals beta, so beta link servo beta, and then A26 equals lambda, link servo lambda. I'm a bit scared of making a video about how I got these because it's pretty involved. Okay, so lambda should be 172. Indeed it is, and theta 2. Perfect. Everything's perfect. All right. So now, actually, sorry. This is. I'm kind of like a bit scared of using my servos for these, cause like what if I mess it up, right? Anyways, now we can go from x, y, z coordinates to servo angles, and actually we have servo on hip for the hip servo, for the knee servo here, and we're missing the shoulder servo, and I think that's omega, if I don't remember correctly. Omega is basically the omega. So that's our 3 servos there. So that's basically what we need. Again, these are our inputs. No, sorry. Yeah, target. Sorry. Defining our constants. Our system constants. Let's clean the code a little bit. I'm uploading this to GitHub, which is publicly available to everyone. Actually, let me upload it here. Slay. This message commit slay. Instructions. All right, so for these inputs, you can basically solve. Okay, and so now let's define variables that make it clear which is the angle for each servo. Servo shoulder deck equals this. And then here, servo hip degrees equals this. We can move this here. Yeah, it's here, and then servo knee degrees equals this. Perfect. And then we can print here. Print angle of the servos. Oh, sorry. Angle of the servos. And it's like hip. Actually, let's see that. Angle of the servos. Modify the last print statement to better name which angle is associated with each servo. And then we have that. Now, of course, let's spend some time, like we said at the top, this is for the rear right knee, rear right leg. So let's spend some time thinking of how do we need to tweak these angles to actually cleanly translate. So, right, so shoulder 90, all right. So the way things are initialized, right? So rear right leg, which I happen to have broken, so not the best for the example. Let me grab some tape. I'll fix it right now. I do have a replacement leg ready, but I wanted to finish this code first. All right, I've taped together, or like here. All right, so the way we initialize this is 90 degrees is like this, right? So it's not like this or like this. 90 degrees is when the shoulder is straight. So we don't have to change servo shoulder degrees. It's already 90 degrees, which is perfect for the target we've set, which is X, Y, Z. If you look at the Y, that 48.55 is the distance between the center of the hip and the axis of rotation of the shoulder joint. So 48.55 equals just the leg chilling. And then next we have, looks like it wants to take the hip to 67. And of course, the way the servo initialized hip is like 0 here, right? Like that's 0 for the rear right. And if we look here, yeah, that's what 67 is going to look like. So it's not actually measuring, like it's measuring from the vertical line, right? So we need to basically subtract. So we need to measure from here, the horizontal. Oh God, from here. This is the angle we want, 22 point, that one, not 90. Okay, so how do we get that one? Well, it's obviously 90 degrees minus 67, right? Because this has to be 90 degrees. I mean, that would work for this one. Servo hip degree. So it's like 90 minus this, right? So if we rerun this, now it's 22 degrees. It's kind of what we want, right? And then the knee, said we have the knee. It's actually initialized here. This is 90 degrees. Pretty sure. I am pretty sure. And so we said we want 100, sorry, actually, let's see, we want 172 degrees, right? And so I think we basically want to measure from here. So it's 180 plus or minus 90, depending on the side. It's gonna be like 180 minus this angle. and it can be plus or minus 90 depending on the site. No, this cannot be negative. It could be 7 degrees. But I just don't think that looks like 7 degrees. It's like, it either measures from here, because that's 90. Let's try that. Oh, 82. Could it be 82 from here? So it's either 82 or 97. So either it's minus 90 or plus 90. I honestly have no clue. All right, so let's see if we input these onto our servo, if the leg looks roughly like this or exactly like that. So let me, hook up the cameras and the robot, and I'll be back. All right, setting things up here. That's a robot. It's been so long, I almost forgot how to set things up here. So I'm gonna turn it on. I think the last firmware we have is it trying to stand in 3 legs and rotating its body a little bit. Or maybe like trying to step here. I think it's gonna clash with the USB. Let's see what breaks first, my USB or something else. Anyways, let me reflash the firmware. We we basically do not care about any other leg other than like the rear right leg. So I need to connect these to here. First things I'm gonna do, I'm gonna probably flash some blink just so it stops hitting the whoa, I just wanted to stop hitting the USB. I think this is the last code we were running. I'm just gonna open blink here. It's very painful. Give me blink. Just give me blink. Alright, well, blink is not working, so. Okay, that's odd. That's so annoying. Charging 5, stand. So we have some code just for it to stand, supposedly. So. Man, I think the Arduino IDE basically, it's not working. Let me reopen that. Honestly, one of the big reasons I want to move to Raspberry Pi is to not have to use this IDE anymore. Oh look, I have a JavaScript error. Huh. I actually have no clue how to fix that. For now, let me just detach that servo. It's fine. Don't want to have to detach it and have to figure out how to reattach. Anyways, the Arduino IDE appears to be broken. Not clear why, but I can't open new files. I might have to like do the old restart my computer thing. You know what? I want to do the update here. Maybe. I mean, I doubt that the update's what's gonna make a difference here, but close and install. All right, we're installing an update, I think, for the IDE. If we switch to Raspberry Pi, we can just upload code from VS Code. And it'll be Python, and it'll be great. I think I don't know if there's a way to upload to Arduino over VS Code. There must be, but I'm not sure. Okay, so these reopened allegedly because things are good now. So I'm gonna upload this code. I'm gonna try to connect to the robot. It's not connecting. Classic. Yeah. What about now? Now it's connecting. All right. Why does it connect when only when I turn it off? Who knows? Not me. Definitely not me. I do not know. Anyways, finally got it to stop trying to destroy itself. And now we can manually. We'll first do it manually, and after we might try something else. But the rear right shoulder. So the rear right hip to 22 degrees, and the rear right knee to 82. And let's see what happens, right? All right, and would you say that looks like? Oh my God, can't wait. Would you say it looks like this? I mean, kinda. And so we initialized our servos correctly, which is good. And I think we can use the same value. Let's check. I'm just trying to. I think we can use the same values for the front right. Right? Let me think about that. Yeah. Yeah. I mean, we keep clashing with the USB, so we do need to fix that on the next design. But okay, cool. Now let's do some thinking and try to figure out what. Actually, let me turn this off. I'm gonna route the Arduino from the top. It's definitely not good to be clashing with your microcontroller like that. I'll just route it from up here. And it's honestly the same thing. All right. Can you even tell? I feel like the contrast is a little high. Is that better? Anyways, so that appears to be working for the right side. Now let's think of that left side, right? What does the left side look like? So if we go back to our VS Code, first of all, single leg. I'm gonna rename these to single leg right. Okay. This is for the right. This is for the right. Right. So this works to the right. Now, if it was for the left, it wouldn't be minus, right? It would be, well, actually, why was it minus? It was minus because also I lost my mouse, so I'm using trackpad now. So it was minus because we were measuring from here. But so, where like this here, the horizontal is 0, but on the left, the horizontal is 180. I'm pretty sure. So if that's 180, we're actually measuring, I guess, from here. So it'll be 180 minus this angle 22. So 180 minus 90. That'll be the same thing. So we like 90 minus that equals these. Oh yeah, no, I got that completely wrong. Wait, did I? 180. I think we don't need the 90, it's just straight 180. Right, so left. And then for the knee here, instead of minus, it would be plus. So if we run this, single leg. I should not have renamed this single leg. Okay, so the knee went to 262, which makes no sense. The hip went to 112, which could make sense. Why is the knee so high? So let's think about that, right? So I'm on trackpad, so I don't know how to, oh my God. I'm gonna buy a MacBook Pro just to have more ports so I can connect my mouse while having Arduino also on. So 172, right? And we measured 90 from here. We said this was 90. I don't know if our equation for the right side is, I don't know if it's actually working. 82, I mean, that's basically flat. Yeah, so horizontal here is 90, but we want, right, 90 from, which is, we're measuring from here or from here. So if we're measuring from here, we want 82. If we're measuring from here, we want 97. For 172 to go to 97, that makes some sense. Basically 74 degrees. Just doing some math here. So that's 90 degrees for sure. But 98, 172, 98. It could be 172 minus 90, 82. So 90 minus 82, 8. So it's like it's like 180. No, sorry, 102 minus 90 gives you 82 degrees, right? The angle we already have. And 82 degrees. And then it's like 90 degrees minus this plus 90 degrees. So 180. So 270 basically is 270 minus and that gives us those values there. And let's try it out. So I want to rotate this guy so we can get a better view. Why not just you also me too? You can actually see it. It doesn't feel particularly stable, you know. Anyways, rear left hip is going to 112 and the knee to 97. Let's see, rear left. Oh, I made a typo. I made another typo. I'm sorry. Another typo. I'm sorry. It's like 4 typos in a row. I'm kidding. All right. Well, that's wrong. That doesn't look like our sketch. Yeah, the hip is completely off. Let me just relax it here for a sec. Why is the hip so off? I thought that would be correct. 112 degrees. Oh man. Unshaped, how to drag in a sketch trackpad. Anyways, and you basically gotta rotate it, but now 180 is here. So if we're moving down here, this is 180. Moving here, I would expect this to be 180 minus 22.85, 180 by 22.285, 157. Is that what it was? No. So we have this angle. So it could be 180 minus 90 minus that, but that can be it. It's like 180 minus 90 degrees minus 67.15. But that gives you the same we already had. Now if it was 0, it would just be 90 degrees minus this equals that. But no, this one's 190 minus 190 minus okay, so it's 90 plus basically math 157. Let's try it out. And if you're lost, I'm sorry guys, I'm just figuring out which way we have to rotate stuff. Shape rotation. All right, rear left leg should now look good. Very good. Yeah, I would say that looks good. Right. Cool. Okay. Okay, so if that works, then we should be able to create a function where we provide 3 coordinates and it spits back the angle that we need on the servos. Right? So I want to ask the AI for help here. I want to say, I want to, okay, so in the following code, we take a series of inputs, of constants and inputs, and calculate servo shoulder deck, servo hip deck, and servo knee deck. These servo degree variables are used to drive a robot. I want to define a function where we specify only the input X, input Y, and input set parameters, as well as either left or right, and it returns the angles. Can you help me with that? And it matters if it's left or right, so we know, you know, which way we need to offset our angles. Well, this is very slow right now. This is a Nucleot Sonnet model. This feels very slow. I think something might have broken. Oh. There's some issues with the API. We could always just use the different model. Let me reattempt. Trying to attach the code. I think I've broken the extension. Yeah, still thinking. Huh. What if we ask ChatGPT? I'm gonna turn on the canvases. Okay, side. See, this code is okay. Let's get started with this. I'm gonna create a new file. IQ single line. IQ function .py. Okay. Gonna bring some of my stuff here. Okay. Yeah, we can merge these angles, I think. Also, we didn't specify one for the shoulder, but we will have to. All right, let's try this. For 8.5 is equilibrium. Okay. I think this works. Okay. Let's run one more position just to validate that things are indeed working. And this sketch is really the best way I have to do this. So 120 and then 60. So 60 and 120. Oh, hip went negative. Hip cannot be negative. So see, we might have to impose something for, you know, oh, hip angle cannot be negative, for example. And we actually have a lot of values that we know must be restricted. All right, let me upload these, manually upload these to the rewrite. So 1 degree and 91, and it should look like that. The rewrite should look like that. And guess what? Indeed, it looks like that. So our function appears to be working. Let's try it again. So let's see if this code actually works. So let me just add a print statement here for link servo beta. And I want to print okay, let's run it. 1.54 print it in degrees, please. 88 degrees. That seems wrong. Oh wait, that's correct. Okay. Such a downer. All right, let's do the classic 200, 100. And if ChatGPT fixes this, that'll be great. 86. That seems wrong. Yeah. Should be 93. The other thing is, like, if this is if the beta angle is breaking, what other angles could break, you know? Let's see what it changed. No. So I don't think this will work because math lesson will never return an angle greater than right? That's kind of obvious. Kind of missed that. Okay, I hate when it does this. It's screwing my so it replaced my sine with an atan. How did you know which parameters to use? Well, actually, I don't know, it's not gonna work. It's like, this is basically math, so. I am a little skeptic here. Yeah, it's terrible. No, beta dog. I don't care about alpha. I care about beta. Huh. No, it's terrible. I don't think ChatGPT understands. I want my original code back. We might just have to big brain this. Sheer power of brain. Robotics. Let's Google robotics. A10 can handle over 90 degrees. All right, here we go. Oh, that's a cool robot. No one said A10 though here. All right, more ChatGPT. I am struggling with the inverse kinematics of a robot that depend on the A10 function to calculate an angle. My angle can range anywhere from 0 to 180 degrees, but A10 is only able to handle up to 90 degrees. I'm having the same issue with the asine function. Okay, so let's see. How is this commonly done in robotics? I imagine it's a very common programming issue. I'm not satisfied with these answers, guys. I guess one way of doing this would be to, yeah, I mean, there's some obvious, I don't know why ChatGPT is not suggesting these obvious ways of doing this, but we take the value of everything in here, right? Print this, and if that is greater than like what, greater than half pi, in this case seems like it's not. If it's greater than that, then pi and a half, which is 3.14 over 2, it's 1.57. It's really not greater than. But if it was greater than, so maybe this is not why it's wrong. Let me see what this angle is like. 31 degrees. And we're happy with alpha being that. Yeah. So beta is wrong. Okay. Beta 93. Let me do the same thing here. Let's see if this gives me a different result. Huh. What's the AC? What's the inverse sine of? I kind of like don't see where's the issue here. It's like I cannot blame it on my functions. 1.53. Oh. I obviously cannot even blame it on the on the A10 async thing, because like we're not even going past half pi, so that's not the issue. Or like at least we technically are going past it, but the values inside of it are not going past it. So maybe I need to go for lunch, take a little break here, but so beta, which is this angle, so sine of beta over L4, which is this, equals sine of alpha, which is this, over L, which is this. Constant, well actually not a constant, but so beta equals the arcsine of L4 times sine of alpha times over L. How can that be wrong? 22. And everyone agrees that the sine rule applies here. Am I that like rusty? Yeah, I mean, that's exactly what we're doing here. It's very simple. I don't know why it's not working. Use the sine rule to find the opposite angles in non-right-handed triangles. The angle is to determine. I guess here they're like splitting the angle. The thing is, like I said, I cannot even blame it on like the contents of these in here of the arc sine are not even half pi. So how could this be an issue? And people are saying that this does work for obtuse. Maybe we should watch this video. Okay, well, we know the issue here, basically. Can go past 90. I don't know how to mathematically fix this right now. I literally cannot think of something. Just because it just doesn't feel wrong to me. I don't get it. I guess, oh, I guess I kind of get it. Is this the actual angle? 93 point. Yeah, okay. I guess I kind of get it. Yeah, okay. Now that I think about it, I do get it. This is under pi 2 because we're already, we're already on the other side. And the actual value we're looking is on the y-axis. So, you know, it's something like 0.92. So we could be here or we could be here. And we're clearly here, but we think we're getting the result for here, for this angle, but we need the one here. And so what we need is a way to determine whether we should be using the arc sine or pi minus arc sine, right? And I feel like there's gotta be a pretty easy way to do this. Again, just this is all high school stuff, guys. I haven't done this since high school. I need to think here. At some point, I want to switch from a sine to pi minus a sine. How can I figure out what that point is? That except I understand. A10 Maybe I should understand A10 too. A10. How can we relate A10 to A sine? Man, I feel like ChatGPT is so good at making it sound like it knows what it's talking about, but not really. Oh. Okay, what if we just think a little bit? Could we calculate both angles? And we had both. How do we figure out which one makes the most sense? We could sum it up with the other angles and choose whichever gives us 180 degrees. I feel like that's kind of like it's not ideal, right? That's kind of dirty. What else can we do? I'm just Googling math here. This is getting embarrassing. Okay, well, the best idea right now is to add all the angles here and pick whichever sums to 180, plus or minus, you know. That will not always work. You could kind of picture it's just a small angle where both are very close. Yeah, we could also map out, I mean, we can't really map out the trajectory. Yeah. Man, I didn't see this one coming. It feels very simple though. Let's see if this came back. It did not come back. Let me restart the extension. Actually, I'll restart. Nope. I know. Oh. Oh my god, I know, man. I know. You're already here. You're already here. I promise you. Yes. Great. Okay. Looks like double is broken right now. Which is it's a shame. It says all services are online. That's a lie. Anyways, looks like this A102 function is really good. So however, this A10 result until see the angle. Okay, using to infer A10 results. A10 effectively combines the logic of A10 and the quadrant check. Okay. Okay. Well, let's try it. Let's try it. Okay. By the way, sorry if I feel like I said some stupid things there. I was saying it doesn't make sense, but now I see that it does make sense. All right, let's try that. Trace Morrison. It then expected 2 arguments code 1. I thought I sent it 2. That's weird. Math A10. My brackets are some bracket. Alright, so the A10 is 0.89. Right? If x okay, my A102 came back as, what does this mean? Alright, so if A102 return that angle in radians, here's how it breaks down. 46, this puts in the first quadrant. There's no need to switch. No, that's not true. Maybe I did this wrong. I probably did, to be honest. Like, the other thing we could do, couldn't we take the derivative of the sine function to see if the slope is positive or negative, and position and pick a quadrant that way? Yes, you're on the right track here. So yeah, obviously, yeah, use the slope. So how would we do it? I think I'm gonna go for lunch. I'm more in circles, and this is this is embarrassing. We're very close, but you know, little math issue here in the way, and can't seem to figure out how to solve it. But it feels like it's something very simple. This shouldn't be taking that long. Yeah. So I'm gonna go get lunch, and I'll be back. All right, we're back. I had lunch, and I had a revelation. Well, not really, but I was looking at the math library for Python, and again, I think a lot of these things are obvious. So, you know, maybe I'm sounding repetitive, but we're using the A sign, reverse A sign, yeah, arc sign, and the results are fixed between half pi and pi and a half. In this is radians, so in degrees, that's minus 90 degrees and 90 degrees. Now 90 degrees, it's not enough. In this case, we are already seeing cases where we're going past 90, but we're actually never going negative. So this minus 90 is unused. On the other hand, A cos, arc cos, or inverse cos, the results can go from 0 to pi, which is 180 degrees, which would cover this case. And so I ran a simple test here. So previously we were using the sine rule to calculate beta, but what if we used a cosine rule, right? So I had this here, and it actually works great. I get 93.4, which is exactly what I had before. Now let me try it on a different angle. So it should be 78. 78, yeah. So it matches. It's perfect. So I'm gonna switch to cosine, to the cosine law in the code. And to do that here, we basically look for link servo beta, and here this is the new equation, where AC26 is L. All right, so link servo L. This is math. C15 is a constant. C15 L1. Oh. Link servo L1. C18 constant L4. C15 L1. Sorry, C15 L1, and then AC26, it's L, I think. Yeah. And so with these being the new equation, we should be fine. Of course, we're going to run it and check, but it should be fine. Yeah, let's try it. Beta. Oh, sorry. Wait. Oh, oh, sorry. I executed the wrong file. Oh. It's a typo. Beta 893 degrees, right? So that fixes the issue. I don't know why this took me so long. I'm sorry. Let me see if doubles by. No, not really. Is it bricks? Seems. Oh, there it is. Hello. I'm not logged in. Oh no. Anyways. Now we're gonna, with this new code, we're gonna redefine this function here. Please output the full code as if it's a new file. Keep all of my relevant comments. This new Claude 3.5 model seems to be pretty good. I've read a lot of reviews, but I also kind of like stopped coding as it came out, so it's a little slow, that's for sure. All right, let's put this here. All right. So I guess we can try this again. And so for angles 100 and 200, for these coordinates, we should be generating hip 26, and let me just triple check here the cat. So to achieve this position leg on the rear right, we should have those things. Now let me connect the. I'm gonna connect the robot again, so you can go back to sending comments. And rear right leg is what should be obvious which one it is. Anyways, let's see if we got it right. Let's see how it looks this time. All right, so rear right hip should be 26 and 116. So you can notice there was a small change in the angle. Now, would you say that matches this? I would say no, but okay, let's try something else. Let's try another position. So let's bring this knee down a little bit, something like that. Can we do that? What would that take? Of course, right now I'm calculating on VS Code, then going on the Arduino IDE and writing it here. Eventually, we're not gonna have to be able. We won't have to do that. It will all happen on the Arduino side, on the microcontroller. This seems kind of suspicious. I'm not sure if it's actually following the animation or not, the cat or not. Let's try something. Okay, obviously that's too much, but let's try something like that. 100 and 150. 4 and 104. I mean, I guess from your angle, yeah, I guess. How far back can we go? Oh. 200. Actually, we already tried this, right? This is one of the first things. 250. The other thing I want to implement here is the safety envelopes we have to make sure we're never mandating an angle that's gonna break things. That definitely doesn't look like it. 250. All right, so that doesn't look exactly correct. As in, like, the robot doesn't seem to match the drawing here. But let's just keep pushing it to see what happens. Well, actually, that already breaks the linkage on here. Let me see if it reacts to that. So 56 and 103. There might be one more variable that I'm missing here somewhere. Yeah, so I mean, that did make sense. Doesn't look exactly like the drawing, I think, but it made sense. Let's try 10 there. And after that, we can try the shoulder, and we can see if the shoulder direction. Oh, wait, well, obviously there won't be. Both shoulders cannot be correct. That's impossible. But we can start to fix it. See, I can't tell if that actually changed. I know it definitely did. 62, 88. Okay, definitely a way simpler method of interfacing with the robot. So let's try the other variable we have here, right? So we don't want 48.5. I'm gonna comment this number because it's key. I don't want to lose it, but you know, let's try something further out, like 80, and let's run this. And so it will not only be our shoulder that changes, it will be multiple angles that change. All of them will actually change. So we have 67, because they're all changing in space, right? So now we're dealing in Cartesian coordinates on a 3D space. So let's try that. It should come out towards the camera. It did come out towards the camera, but not enough. I want more. Let's see. By the way, that also tells us that our shoulder angle is correct for the right, so we'll have to flip it for the left. So let's try something crazy like 220, 120. I don't even know if this one's possible. This is the one actuator that we didn't map, so we get a little bumpy here. Let's see that. Yeah, that's decent. Let's try something safer and then push the shoulder a little more. Something like that, 180 on 50. 180. 80, 50. And these can come out to like 200 or something like that. Yeah, let me try that. Let's see. Yeah, so it's definitely working as intended, and it looks very cool. Maybe it will make sense to build like a better GUI, like graphic interface for humans to be able to almost like animate movements on the robot. Because, you know, doing it this way is a little painful, but this is very cool. It works. Now, without even seeing anything, I'm gonna say that this is correct, but for the left side, it won't be this. Right, so if we're right now we have been adding and it's rotating this way. If we add, it will rotate the other way. So we want to subtract. And so it's 90 degrees straight. And so we want, I guess, 126, 90, 37. We want to subtract 37. So it's 90 degrees minus that. No. Is it? Okay. Okay, so 180. I think this would be do it. This would do it. Okay, so let's try doing this for the left. Let's see if it works. All right, so rear left, rear left shoulder, right, 52, hip 111, knee 74. So you can't see it, it's on the other side of the camera, but let me rotate it so you can see it. All right, so this leg should mirror this leg. And I made a typo somewhere, classic. This is like when you're jumping between languages and like you miss a comma. Perfect. First try. Easy. All right, guys, we've mastered inverse kinematics. Now all we have to do is basically, I don't know, draw whatever the robot taking a step looks like. I guess port the VS Code to Python to Arduino. Or should we add the safety stuff so we can never break stuff? B0. I don't remember. Okay, this is terrible, but I don't remember. Where I put the safety stuff. All right, ignore for now. I guess translate this to Arduino. It's like the natural next step. Let's see if the AI can help with that. I have the following code in Python that calculates the angles of servos in a robot using inverse kinematics. I want to be able to upload these onto an Arduino Uno microprocessor. So this needs to be an .ini file. Can you help me with this? I have also attached stand.ini, which is which has my Arduino servo wiring setup. So this is pretty vanilla, I think. All right, let's see what comes out of this. Okay, Arduino, yeah, Arduino, I know. Let me help you remember the math. Please output the full code and keep all relevant comments. I want to be able to upload this code to Arduino. Okay, I do wish generating code was faster, but it's pretty cool that, you know, we're at the point where AI can just generate this code. All right. Have we generated enterprise value today, guys? That's the real question. Oh, it keeps going. It's a lot of code. Of course, the way I see all of these things, you know, even if I spend half a day, that's cool, troubleshooting, let me see how this works. Even if I spend half a day troubleshooting an inverse kinematic equation, my belief is that I'll be able to use this knowledge in the future to create more robots, and so this is actually good. All right, so constants. Okay, I think it got rid of the left and right stuff. We accounting for the different angles for right and left side. Okay, so it added a boolean is left side, different collisions. Okay. Calculate left side. Okay. Okay. Now the way this would work, so the way this would work, so we're back to attempting to walk, and it's like, okay, how do we actually do that, right? Like lift square, and we can try it. I think we're at that point where it's like, okay, what motion do we actually want? Robot crawling, quadruped robot crawling. I guess what was this video here? I remember the horse. Trot, crawl. All right, we're gonna crawl. You lift. Wait, you lift. Oh my god. Okay, you lift. Okay, walking sequence. 1, 2. But what's a walking? Right? It's like no, because you won't go forward if all the other legs are. I guess it's like you move one leg up, you move another leg up, the next one, and then right? Quadruped robot crawl. I feel like that makes sense. Oh, you know what? Stanford Popper. I mean, I don't think these guys have a good walk, but oh, actually, this guy has good walk. Feels like the robot's very excited here. Popper V2. Oh, they moved to VLDCs. I think it's trotting and it's on walking. As in, like, there's two legs moving at the same time. Yeah. Like kind of like a diagonal walk. And then the other thing is, how do we actually want it to walk? How do we actually want to walk, you know? I'm gonna disconnect from the robot a little bit for a while. Need my mouse, not enough USB ports to use mouse and screen at the same time, and robot. All right, so gonna driven, right? So basically, if this is a ground somewhere, you know, you wanna like go up. Something like that. It's definitely like go up and then eventually push back. You push back when the other set of diagonal legs is going up, I think. So it'll be like here. Well, I mean, now we have to map it in as angles, right? So it'll be here, like a triangle. So it's not a, well, all right, so it's not a square, it's a triangle. And I mean, and every parameter, like, I don't know what the ideal shape of this triangle is, but here, or we could even start here, bring it back. Alright, so start here. I need it to be fixed. Fix. Alright, so you can start. Oh my god, guys. Just fix it. No. No. Anyways. Oh my god. No. Anyways. Okay, so here. Go here. Go here. And then move here. Right? So 3 positions. $195, 35. I'm just completely making this up. Completely making it up. Oh. Yeah. Okay. So that'll be the points. So here, here, and then here. Okay. Okay. So I want to tell the AI here, great, good job, that looks good. Next, I want to pass 3 different sets of inputs and have the robot loop through it. This will only be for the right side to begin with. Can you help me with that? Our servos. Okay, let's see if I can do that. I mean, I don't think this is like the ideal. This feels very hard coded. It should be on a loop here. All right. So now we have to define these positions from the hip. So I think it's like 7.5, 2.5, and then again, like I need a cleaner way of doing this. 195, 195, 35, and then oh, is this a negative actually? I guess that's negative, right? We haven't tried negatives so far. 225 minus 5. 225. I don't know if it'll explode. All right. Well, that's moment of truth. I have no clue if it'll explode. I mean, why would it explode, right? Okay, it's doing this weird thing where it won't upload the code when the battery's connected, which is very annoying. All right, let's see. Cool. Does that look like a triangle? Looks like an inverse triangle to me. Why is our triangle inversed? Oh. Wait. I actually have no clue. But it is a triangle, right? Gonna get a drink. Alright, let's write some code to better walk. I also suspect that we can improve the how we find the feet in the Cartesian coordinates. Might not be fully representative of reality. But okay, so let's see. I think our triangle needs a longer base, first of all. Something like, I don't know how long can we go, but minus 40. And 110. Let's try that. We'll always also make the movements more obvious. Okay. I think we're bottoming out there somewhere. Yeah. Here. Yep. Okay, rolling back the changes. Okay. I want to be able to know which servo is getting what angle commanded to it. Can we pass these on the serial monitor? I want to make sure the angles are being calculated properly. Just because the Arduino code looks a little complex. I don't know, I personally prefer Python, that's it, that's the thing. Stay in forever. Okay, and let's see which serial, okay, that's serial. You need to know which serial frequency it's looking at, so monitoring. Okay. Oh. Okay, so I want to compare these to the code I had here. It's all commented out. Okay, so let's see. So these are all rights, and you know, the angle is 75, 48, and 225. And so what should these give us? 90, shoulder 90, hip 39, knee 18. Yes, that's right. 35, 195. Save, run it. 90 degrees, close, tape 83. All right. And then last, -5. First time we run a negative, so I'm curious. Shoulder, hip, 90, 90, 75. All right. So the Arduino code is calculating the angles correctly. Yeah, we just need better angles, I guess. So I don't know, bring it. Oh, bring everything. Man, I have like no clue what I'm doing here. 180. 75, 35, 40. Okay, we'll find a cleaner way of calculating these things. Let's try some new angles. Let's flex the leg a little bit. So so 40 and 180 and 35 and 150. Sorry, minus 40, and this is 110 and 180 also. Alright, so let's try that. Maybe we need a square, not a triangle. We seem to be bottoming out in one of the I can't tell which one. Oh, on the one. That minus 40. I cannot. Can we actually? These should just move vertically. So that should be a perfect vertical line as far as the robot is concerned. So maybe, right, there's only Z axis range here. So I wonder if, I mean, we could add more points throughout the motion to smooth things out, you know? Can I get rid of these? And instead, let's try a little square. And 50, 50, 180. So move here, 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 right? Let's try a square. So there'll be 4 positions now. And it'll be, okay, so it'll be 20 and 180. And then it'll be 20 and 180 minus 50. And then it'll be 20 plus 50 and 180 minus 50. And then it'll be 20 plus 50 for 8.55 and 180. Okay, let's run that. Oh no. Let's try that. So this is a square. So it's obviously, so the x-axis is a little off. The y-axis is a little off. Such as okay, but it's, I mean, it's technically doing square. Well, the camera's sagging a little bit. Technically a square. She's a little off. Now, one of my ideas to fix this is these here, right? 143, but it's like, let's measure from where? And the thing, because it wasn't clear where to measure from. By the way, what happens if we speed this up? Right now there's a big delay. Let's cut the delay in half. And if it sounds a little crunchy, it's because the leg is broken. I just taped it together. Yeah. So I think one of the questions was, I mean, if there's one axis of rotation here and then another one here, right? I mean, this distance obviously is, wait, gotta constrain this. This was obviously, why is this not working? Uh, 37, right? So if we look at our sketch here, 37 right there. But the other one was, you know, if we were to keep this a straight line, which we did, straight line, it was like, okay, where do we put it? So it was like 143.8, 143.827, right? So you can see that the point where we're moving the leg around is here. And it's not quite here, right? So that's where we're moving the leg from. I really want to get it walking. I mean, I still think it is a square. I want to ask the AI, can we smoothen the motion by extrapolating points between the defined positions? Fixing, okay, fixing. Oh. Wow, it's interpolating a lot here. So applying the changes. I mean, yeah, definitely feels like a way better method to interface with the robot. Still haven't quite like nailed it. Use these positions. I don't necessarily like interpolation. All right, upload this. The other thing is what we were saying last video about like, or like earlier this video, I guess, like last week in my time, about trimming the actuators. It could be correct. All right, let's try this. So they should be smoother motion, or should be interpolating. Oh my god, that is so weird. It almost feels like it's alive. Pretty cool. Honestly, like still, well, not gonna use that, but pretty cool. This should be enough for now. I mean, this works. It's now just a question of like doing the work to get us right. We're comfortable with. And like right now, the best way of doing this is this. The best way I have of doing this is this. So let's try this. We can definitely build a better. We could build some sort of GUI, some graphic interface. But man, like That's like a side quest I don't want to go on right now. Minus 70. 180. All right, we made the square a little bigger. Rectangle, technically. No, still needs to come more forward. So like maybe 30. No, minus 30. Right, so we gotta go here, maybe here. All right, minus 40. Let's try that again. Okay, so I don't think the negative angles are coming through. What do we make these zeros? Because I'm making it more negative, but it keeps going backwards instead of coming forward. It should be coming forward according to our axis of the way we've orientated things on CAD. Yeah, very little change there. Basically no change. I mean, the angles did change, but it just kind of looks the same to me. Let's try this. So there should be movement only on the x-axis. Let me try a separate leg. Front right shoulder, front right. Let's move to the front leg. Front right. Okay. Trying to see the full range of motion on the x-axis. Holding y steady, supposedly. It looks very diagonal to me. Yeah, it's not really holding it steady. It's kind of odd. Oh, I do wonder if it's because of the offset that we have here. Trying to imagine the offset. I feel like it'll still be diagonal. It's like our axis is slightly off. Why could that be? Like, where did we define the x-axis? Let's keep increasing the range of motion here. That doesn't make sense. I mean, we've validated the math, so I don't know why this is not making sense. That just hurts. Yeah, the negative is definitely producing the wrong stuff here. Let me try again. I know I already tried these, but so minus 30, and then 180, 45. Right? Okay, well, let's try it on cat. 180. The 47. And the servo 54. Seems to be doing it correctly. Okay, let's try some basic stuff here. Let's move to the standing position, and then front right. Let's move this to 46, 47, and 54. So it's not making sense. Yeah. Yeah, that's wrong. That's wrong. But why is that wrong? Because actually, let me clean this sketch a little bit here. Why is that wrong? Because 54, right? 47.92. Yeah, actually, let me put it on the spreadsheet as well. So 180. So minus 30 and 180 should produce 42 degrees at the hip. Where is it? Are we not measuring this? Oh, 47 at the hip. This thing is 42 minus 30. Right, this is the hip. We measure here to here. 47. Okay. Now if it's 0, I'll be correct, right? Oh, I'm gonna disconnect from the robot. I need my mouse. Okay, this is good. We might have caught another bug. It only takes hours to fix each bug. Hip 52. Right, this is a hip. Something's very broken here. 180 and 0. Okay, what about 10? 10. $55. What about minus 10? What about 10? Either or is just wrong. Minus 10. Oh, I guess this is the hip angle. 55. It might be just a simple notation issue then. Okay, so 10 and 80 produces 55, right? Yes. 10 and 80. $34 and 70. 34 at the hip. 34 at the hip is correct. Okay. What about minus 10? Sorry. 10 the other way. Minus 10. 40. Yep. 49, which is here. 49, yep. Alright, what's working? Okay, wait, but what about those angles that were producing complete nonsense? Where is it now? I guess I overrode that, but it's in VS Code here. Right, these guys. Minus 10 and 180 was nonsense. Of course everything works now. Okay, minus 50 I think. No, 50. 50 and 180. Let's try 50 and 180. 65. Oh yeah, see, this is wrong. Okay, so there's a point where this breaks. 65. Okay, so that's good. I wasn't hallucinating. I mean, it's not good because I don't know how to fix it, but I imagine 55. Oh, this is kind of correct. How can that be? 35, 65. Oh, because it's minus 50. 34. Oh, so it's not broken. Okay, so I was hallucinating. Great. Okay. Well, if that is the case, show me what that looks like in here. I need to reconnect the computer to the robot again, and I lose my mouse again. It's very cool. All because Steve Jobs couldn't give us more USB ports, guys. Minus 50, minus 50. Minus 50, minus 50. And 180. Okay. So if we upload this, it should go to this position where clearly the feet is in front of the hip, right? Clearly. Oh my god. Okay. What if we fix this like this? I don't get it. Right? You think this is very possible. Very possible. Let me put some safe code here first so the servos don't melt. But let me save these. Let's go check that we're not breaking the safety envelopes. Shit. Right, so the hip is 49, the knee is 39. Oh, we are breaking those safety angles. Okay, I see the issue. Okay, so how can we, how can we keep this in mind when designing something? I guess I guess we could use forward kinematics to translate these angles onto an envelope. And you know, as I say that, I have no idea how to do that, but I know it's technically possible, right? So yeah. I don't know. Okay, for now, let's define it. Let's define. Well, okay, I don't know. I'm like, just a lot of ideas on where we could go from here. I'm a bit shocked that that's the issue. So hip 36, hip angle 36. Right, we can't even go there. Honestly, very tempted to call it a night here. I think it's been a long day. 32:46. Should be fine. So minus 20 and 130. At least we know what's wrong, that's always very comforting. Even though we are not super clear how to fix it. I mean, it's one of those things where you can just like figure it out. It's just one of those things of like, can you figure it out by looking smart for the camera? All right, so if the envelopes are real, that worked. Now, does that look like these? I disagree. Now, why is it so off, right? Like this is obviously an acute angle, like less than 90 degrees, and in real life is more than 90 degrees. Could it be because it disagrees on these? No. 32 on the hip, yeah. 46, yeah. The knee, like the angles on the servos match our drawing, but the neck doesn't look like our drawing. So what's up with that? Like what am I missing here? The other thing I could try is, well, I mean, we've tried this before, but just try it again, I guess. 32, 46. If we manually write these angles, will the leg look like the drawing? No. No, it won't. I put it on the rear right. It obviously doesn't look like the drawing. So why is it so off? This angle is correct. And this angle is correct. But this looks very off. And why is it so off? And again, is it because of how I defined it and it's breaking the math somewhere? I mean, it's entirely possible. I don't know, kind of like to believe that, because it sounds like an easier fix. Hmm. I'm speechless. I do not know. I have to imagine it's something in the math. I just not exactly sure. I think the hip seems to be perfect. The leg upper, I could believe that's correct. And the shoulder seems to work pretty well. But this isn't following this isn't doing what I wanted to do. So yeah, I gotta believe it's something in the way we've defined the tip of the feet that's throwing everything off, all the numbers slightly off. You know, I was feeling pretty good for a bit there. But not not the case. Okay. I could also just like stop trying to break it and stick to stuff we know works. But that's not as fun, you know. 4. Yeah, I'm kind of like, I'm gonna call it a night here. Let's see what it does. Oh, wait, which one? Oh, I guess from right. Like, see the leg upper moves exactly as it should, but the leg lower doesn't. And so I just have to believe that it's because of, you know, of how poorly I define that that angle. It has to be that. I don't know what else it could be. I mean, it seems like a lot of deflection for what it is. Maybe I design another leg where X is actually here. Redesign the leg. I don't know if that's gonna help too much, because really what I look at is this angle here, the angle of this line, and that's what seems off. But it's hard to tell. So this angle, if we mandate here, the leg will make it look. Yeah, okay, maybe that's not it actually. But what else could it be? Could it be that the trim of the knees is just way off? Right, so for example, we said that 90 should be flat, right? And so maybe we haven't initialized them correctly. That could be one thing, right? So we do 90-90 on the rear right. The knee horn should be completely horizontal. It isn't. Also, that angle should have been saved. Hip 90. Oh, it's not. Sorry, my bad. 50. Right, okay, so the servo horn should be completely horizontal. Honestly, it's not bad. It really is not bad. What about the hip? The hip should be completely horizontal here. Right? So, I mean, it's pretty good. I think it's pretty good. I mean, it's not perfect, but it is pretty good. And so why doesn't it match the cat drawing perfectly? I'm puzzled. Well, let's see. Let's try to recreate this in CAD. So we'll change this to driven, and we'll try to recreate this in CAD. Right, so it will be AK function 122.852 and then 558 no 686. Okay. Yes, it's perfect. Hip 0, knee 90. That's exactly what we have. Does it look the same? See, I would argue it doesn't look the same, but maybe I need to get used to the idea that this is how it's gonna look. The other thing we could do is that now that we've validated this drawing and the math and everything seems to be working, we could also make it so it animates the leg itself. I think that's possible. Yeah, and so that way we can get a better sense of what it would look like, right? Even though I feel like it's kind of obvious that what this would look like. Right? I mean, it kind of looks like, it basically looks like that. But now if you compare with the drawing, it can be a little deceptive. Yeah, I think it's good. I think it's good, but I'm tired. Kind of call it a night. So to summarize what we did today, we talked a little bit about Raspberry Pis. We took all our inverse kinematics math and generated code, and then we started running some basic walking motions on the robot. So we tried the triangle and the square. And next, we'll just keep refining those and try to walk. And as soon as I have something that resembles walk, I want to finish this video. I feel like it's already been too long, but I said I would make it walk, and I'm going to make it walk. So see you guys tomorrow.
A few moments later.
All right, we're back. It's day number 2, 3. I'm not even sure anymore of trying to get this robot to walk. Robot's on the ground right. Oh, camera is all broken. Sorry. Let me fix this. Robot's on the ground right now. Just getting the day started. It's around 1:30 Pacific, and been working on my YC app. So YC apps are due actually this weekend, and I'm probably gonna apply to YC with this robot doc. I've talked about this before, but there's, the idea is basically that okay, there's a lot of ideas. I haven't consolidated really well into a single one, but basically it's something along the lines of we build these robots and create content using these robots, right? So the main product really is content. So that's how we monetize, right? So right now on YouTube, for every 1,000 views, you can get like $5, right? So if you get, I don't know, like 5 million views, you get $25,000, which is, it's not bad. It would pay for the robot, it would pay for my rent if we just go viral one time. But the idea is that with robots, you can create very unique types of content that otherwise would not be possible. Obviously the robot right now looks like obviously a robot, but it doesn't have to look that way. It can look like anything we want, any character from any movie, from any video game. It can be Pikachu. It can be anything. And the belief here, like the core technology that enables this, is what you see here in the frame below me. It's just a skeleton, right? But with the hardware, 3D printed, very cheap BOM, like $1,600. But the same, this body scales to any shape factor. You want to build a gorilla with really long arms and make it bigger? You can. You just need, it's all the same components, just bigger actuators, bigger battery. Same on the controller side. You want to train it to be a dog. It's the same process to train it to be a gorilla. Really, all you have to tweak is you have to design the motions of a character, which we already do to make movies anyway. So yeah, I just think it basically brings animated movies to real life. And I think that can enable a lot of cool experiences. Think of Jurassic Park, but it's real. Westworld, but it's real. And it can create a lot of fun content, like who runs faster, Pikachu or Usain Bolt, that kind of stuff. And all of these kinds of experiences of robots interacting with humans, like, you even have sports, like think dodgeball, but you dodge drones instead of robots and stuff like that. So that's the company I want to build. That's the company I want to create. And I know it looks very simple right now, just a piece of plastic on the floor. Haven't even figured out how to make it walk yet, but we're gonna get there because we have to get there. Kind of like just saying this out loud helps, because I just been writing it down, but saying it out loud helps. Yeah, on the idea of the skeleton that can basically be adapted to any shape factor. If you think of, most mammals have very similar skeletons. If you compare the skeleton of a bird, actually bird's not a mammal, but if you compare the skeleton of a human and a whale, they're actually very similar, right? Whale skeleton. It basically has the spine, it has a mouth, it has, basically arms with bone structure that looks like fingers. It's almost as if like the same design was adapted over and over. Yeah. Let's see if someone else compare. Yeah, see, like there's these kinds of comparisons all the time. A human arm, a cat arm, a whale, a bat, all share very similar, similar structure. And so it's the same idea here. And then the other thing I was gonna say is like, I think like two things, right? So when I talk about robotics and, some of you have reached out, you're building your own robots, that's cool. And I start talking about like, hey, a lot of people seem to want to start a company in robotics, and they start to think of like very practical applications of like, oh, okay, can this robot carry these, do these dangerous tasks and so on? That makes sense, and that's what there's a reason why Elon is building humanoid robots, and there's a lot of money going towards that. And actually, a lot of the robots that exist today have already been going for those jobs. I think that's very saturated. Everyone's going for that. I think there's a lot of value in entertainment. There's a lot of value in making the future better, and a future that inspires people, and also infusing technology into our culture. A very simple example of this, it's like I meet a lot of engineers, and when you ask them like, why did you decide to become an engineer? The answer is usually like, oh, because of the Iron Man movie, or oh, because I toured NASA as a kid and it inspired me. So watching a rocket launch on TV, or watching a movie about an engineer who saves the world. These are ways where how technology gets embedded into our culture and becomes cool to build things, and people can dream of what things we're going to build in the future. And so I think we can do the same thing here with having basically a content studio that runs on robots. I think that would be extremely cool. I think any kid watching that would want to be like, I want to build my own robot. So that's kind of like why I'm motivated. Also from a personal standpoint, like my YouTube channel, if you see my YouTube channel right now, it's pretty empty, right? I have like 8 videos. But in high school, I had in middle school, actually, I had a different channel. And, this was way back when, before Mr. Beast, before PewDiePie. I was in Peru. Like, I barely had a camcorder. It wasn't cool to post on YouTube. No one in my school thought it was cool, but I thought it was fun. And then, I went and studied engineering, and I developed this passion for building things. So this is right at the intersection of two things that I'm really into. I think it's really hard to figure out what you're really interested in, and one way of doing this is like, oh, what would your 12-year-old self be interested in? And the answer in my case is making YouTube videos and building things. Anyways, today we have to get walking so I can record the application for YC tomorrow. I think yesterday we basically were walking. It's just like the motion wasn't as smooth as I wanted. Like, it looked slightly off, and I think we can clean that up today. By the way, I don't know if you guys know what GeForce Now is. It's an NVIDIA service that basically lets you. So I have a MacBook Air. I cannot play any video games on my Mac. It just doesn't have a GPU, and it's like it's a Mac also. Nothing runs on Mac. But NVIDIA has this service where they execute the games on their servers, and they just stream it to you. And it's a really good service. It's like $9 a month, and you can play anything in max resolution. It's insane. But anyways, today they announced that they're gonna cap it to 100 hours per month per user, which sounds like a lot. To me, it sounds like a lot, right? That's like 3 hours a day. But people went nuts. People are going nuts in the comments and on Reddit. And I was just thinking, first of all, I'm shocked that people are playing that much video games. If you want to do that, it's up to you. I'm just shocked. Like, I've never seen that. And I just thought, wow, that's a really, if I had a product, if I had a service, I feel like this is an excellent sign, right? Like, if you limit the usage, your users love it so much that they riot. That sounds like product market fit. And so Replit had a similar situation recently where they got rid of, I think that the free tier, they limited the free tier. There's still a free tier, and they got a lot of pushback. It's like, oh, that's a good sign, at least that I mean, you can always revert changes, but that's super good confirmation that people really like what you got there. Anyways, I don't know. At least that's how I see it. What do you guys think? Just reconnecting here. Man, I'm also like moving places, moving apartments, so like mentally fatigued with all that stuff. There's so much paperwork. Such a silly process. Anyways, so the last issue we encountered last night was that I basically was commanding it to do a square with the leg, and it looked like more like a polygon, like a rotated square. And I thought the whole point of doing inverse kinematics is that it would actually stick to the Cartesian coordinates that I command. So I kind of like wanted to fix that. And I think the reason why it's off is because this, right? So this is how we represent mathematically the leg. It's not the green model. It's the line that represents the leg mathematically. So when we command Cartesian coordinates, we're talking about this point here, right? This point here, the tip. But in reality, probably what we care about is this point here somewhere. Oh, actually, kind of hard to. Well, I mean, this point here, probably, right? That's what we actually care about. Yeah, and so it was a question of, okay, how do we change these? I haven't thought about it at all. I was just like, this is basically in essence what we need to change. And it might be as simple as changing one variable, actually, one constant. So if we go back to our spreadsheet here where we originally did the calculations, the parameter that needs to change, let me see if we still have this open, would be x set g and maybe d. Actually, x, y, those are the inputs, so those do not need to change. and G is a function of D and an input. So really it's only D that would have to change. And D is a calculation of inputs, and 1600, that's a constant actually. So maybe D doesn't have to change. So what needs to change actually? I guess F would change. Where do we use F? Oh yeah, F is used all over the place. And so we can start with changing F. Of course, then the question is, how does this affect the 4-bar calculations, right? Because right now the 4-bar, basically, what is this? 4-bar assumes that these two are in line, right? But if we draw it this way, so if we make a new point here and we draw a line from the pivot point to here, obviously these two are not in line anymore. Actually, they're off by that amount, not a pretty number. So F would be this is a new value of F. But in terms of our pivot point, we would have to change the way we use phi. I don't know how we use phi. Let's see how we use phi. So on the 4-bar here, we must be using phi here somewhere. So for theta, not for theta, theta. For alpha, H26 for alpha. So alpha is pi minus phi, right? So if we go here, pi is 180 degrees, right? So the angle from here, so this angle, if these both are in line, this would be 180 degrees. It says 0, but from this line all the way to this line, that would be 180. So if you sum these two, it's 180. So this is phi, and this is, I think this is alpha. We said, yeah, alpha. Right. So if we change this angle, I think we talked about bringing it back. Change this angle somewhere here. Then alpha is no longer pi minus phi, because it wouldn't be pi. Right? Let me draw it out. Actually, let's see if I can. I want to see if I can duplicate this sketch, because it's always good to have revisions. Can I just copy paste it? I don't think I can. Anyways, yeah. So, and I think that's basically everything that needs to change. So. So first of all, we would get rid of the inline, and then we would make this angle to be that. And then this distance is not that anymore. We care about this distance now. That basically, wait, that didn't change at all. Is that correct? I mean, tiny change. Also, maybe this won't matter actually. Maybe it won't matter that much. Anyways, that's the change. And let's just make sure everything can still move. I mean, it doesn't want to move sideways. I don't know what's going on. What happens if I delete this? Oh, did I might have locked the crank here somehow. I don't see how though. It has to be like, yeah, I don't see how this is locked. Oh, because of these, right? These we said construction. I feel like we don't need that. Oh, yeah, I think we said that's an imaginary line. Okay, that's okay. Why are we fixed? Oh, this. Okay. All right, cool. And so, let's validate these on a spreadsheet first. So we said F is going to change, right? So F used to be 143, and now it's, I mean, it's a tiny change. No one cares, but now this is the new F. Did anything even change? Let's start double. I'm just checking what's going to change because I feel like nothing's changing. Yeah, it's a tiny change. Anyways, so now if we input some numbers here, I'm gonna close this for now. If we input some numbers, say for example, make this driven. So driven means this define the sketch. Sorry, you can make a dimension, a driven dimension. This means it's gonna be driven by whatever, but it's like basically you're actually measuring. Or you can make this a dimension, a fixed dimension, which means it's gonna be exactly what you define. So 60 and 170 here. Actually, let me check which side of, yeah, 60 and 170 should input us theta on the hip of 71.71. Yeah, that's perfect. And phi should be 82. Let me get rid of some decimals here. 82.183, 82.183. So appears to work. Let's see if we got here this correct. So this would be theta 2 174.542 at the end here. Theta 2 is off. Okay, and this is where things get painful. Well, okay, actually no, let's think about that, right? So we just broke the way we defined alpha here, right? And we didn't fix it. And we said alpha was pi minus phi, right? Because this angle would have been 180, but these two don't sum to 180 anymore. In fact, it should be 360 minus this angle here, 173. So it's like, and just bear with me here, okay? So it's like 360 minus this in degrees. But we need to change this to degrees here. Which is pi over 180. So that's a new alpha. And so if we go back here, 174, let me get rid of some decimals. I don't quite remember. 174.542. 174.1542. Perfect. Nothing else broke. All right. Now it works here. Now we gotta update the code, which is, you know, basically we're updating the f constant and alpha. So let's go on VS Code and do that right now. Hopefully this is making sense. Honestly, it's simple stuff. Okay, function. All right, so input no, leg lower. So we've changed the leg lower, I think. Leg lower. Yep, leg lower. So we didn't change the leg lower. There's maybe these two are in the same radius. That's why. Oh, they are. Okay, well that was that was on purpose. All right, so we really the only thing we've changed is how we calculate alpha on these 4-bar knee. So alpha, I think it's link knee alpha, and so and I want to write the full numbers here, which I know is set we don't want to do, but it is a constant. It's kind of dirty. It's probably a better way of doing this, but math pi. So like that. Math pi. Basically this. And we do have to go to the other files here and also change it here. Knee alpha, knee alpha pi. Okay, so this is a different language now, so no more math here. So maybe that'll work. I don't know. What do you think? So now we can check if, you know, if we run these, if we'll look at something closer to what we actually see in reality. And then the other thing that we talked about yesterday, and I haven't fixed yet, is the we do have a whole safety envelope of where the servos can and cannot go before they clash with each other, which we don't want. And I think it's here, yeah. And so right now to draw dynamics, kinematics, how they walk, we're basically guessing where we can go, which is not a big deal right now because, you know, our walking square might be 4 points and it's very simple, maybe even 3, maybe a triangle. But at some point, you know, when we want more complex motions, we will have to build some code to make sure, you know, the movements are permitted. And this really is only an issue with this is only an issue until we move to the ML controller. Once we're at the ML controller, I am pretty sure we can just basically while you're training, just tell them like, oh, make sure no components collide within your body, and these will delete the need for these. This is like a lookup table. It's like dirty, but I do want to move to joystick controls soon, and this is manual, and this will be like just analog joystick, you know, no ML, just regular analog to PWM, and at that point that will be highly relevant, I think. Although I haven't really thought of how to program something with a joystick yet, but you know, it cannot be hard. Anyways, so the next step here, I think. And I should probably write these down, write down the steps. It looks like I wrote some thoughts here. I should write the plan for each video. I don't know if anyone ever comes to this document, but we've documented a lot of things. Anyway, so the plan here is to come up with a new walking square that meets our safety criteria, so it doesn't lead to things colliding, and then executing it and see how it looks in real life. That's about all I can do. I mean, that's how things. That's how docs work. Yeah, and for these, I mean, I was also looking at how, you know, other dogs walk. These guys are doing like a diagonal trot, which makes a lot of sense. I think you can get to the diagonal trot by first crawling. So crawling is one leg at a time, and after that, if that works for one leg, then you can just scale it to diagonal trotting by basically crawling 2 legs at the same time in diagonal. At least that's how it works in my mind. And it's honestly, it's kind of hard to see. It doesn't look like they're doing square. But it's hard to see. It's hard to see. I don't know, somewhere I saw square, I was like, square kind of makes sense. And of course I'm completely making this up. Making it up. No idea what I'm doing here. I hope that's okay with you. Yeah. So we have that, and so from that we can infer our points. What we do need to do is to make sure this is a safety envelopes and stuff. So I think IK function here. So it's just cool because you basically give them some coordinates and it tells you the the angles of the servos. So here I'm just writing down the square we just drew out. 100 height. So you can define 4 points on a square. You don't have to define every single point, just a square. And then it's an x-axis -15, and then base, and it's like 60, right? So we define the top left point, and from that we can infer everything else. And so here, you know, we can do -15 and 100, you know, and it's like so 22 and 38, right? So if we go here and we make our leg driven, and then we put this leg here, then the angles here should be the angles were 22 and 48. So yeah, so this is 22, 67 plus 22 is basically 90. It's just how we initialize the servos, and this one here is 128. So 180 minus 128 is basically 5238. I don't remember how we initialize these ones, but I think it looks about right. Did we just break something there? I got crazy with the anyways, and then the question is, of course, and I do realize this is a terrible process. It's very manual and involves a lot of steps, and it's but then the question is, you know, is for 22, can the knee be in at 38? The answer is yes. Can be anywhere, just about anywhere. Right? So 0.1, 0.2. I'm gonna document this way, but kind of like don't need it. we could write a function for these, so we don't have to like manually type each one. We could also write a function with a lookup table that will tell us if it's safe or not. We could. These are all things we can do. It's just I don't necessarily feel like doing it right now, but you know, if it gets tricky, I'll do it. All right. Okay, so we have top right. So now we go down here. So it's like -15 and 60, and it's like hip 14, knee 35, and then we go here, hip 14. Yeah, just about anything goes. And then we go here, and it's like plus 60, so that's 45, and then 60. We run that, and it's like, well, hip -31, so now it's broken. Let me see the drawing. So it broke it at this point, bottom right, so here. Oh yeah, I see. That's annoying. That's annoying. Okay, so instead, let's write this function that will tell us if something's broken or not. So I'm gonna IK safety check. I'm gonna call it safety check. All right, so I'm gonna talk to the AI here. I'm gonna say, instead of under the comment example usage, instead of calling for, instead of calculating one leg angle at a time and printing its outputs, I want to be able to process multiple different Cartesian coordinates. These can be either through a loop or an array. Let's see, I think it's kind of simple. Example usage, okay, test cards. Okay, but now instead of listing all of the test chords, I want to list a single point and then list parameters for a square. So I need height and base, and from that we can infer the other 3 points. Right, so I mean, this is just like basic stuff. Okay, so click there to apply. Right, so you find a starting point. Let's read the code, but okay, site right, okay. And so now let's execute this, see what happens. Okay, so that is perfect. Thank you. Well, actually, let's triple check the math here. So square base x y z. Okay, just one change. The square height should change the x-axis, the z-axis, and not the y-axis. So just a minor thing. Nomenclature, again, it's like, that's why I was like making comments to find the axis here at the top, because like everyone, I mean, a lot of different industries, a lot of different people have different standard names for their axes, but you know, other than that, it's good. Okay, and now last thing we need is to add the safety check, right? So we don't want to do this manual safety check, that is boring. Okay, all right, thank you. always be nice to your AI. One last thing, I want to make sure the angles that we calculate for the servos of the shoulder, hip, and knee are safe. These are servos in a robot, and under some conditions, the servos will clash with each other, which is not good. Just explain it to the AI. The condition, the angle of, we can use the angle of the hip servo to determine whether the knee servo is in a safe position. These are the safe knee angles for a given knee position. No, for a given hip position. And then we're gonna print this stuff here and I copy paste it. I'm just gonna clean it a little bit. Yeah, it's a little dirty. I'm gonna list it like this. I think it's gonna understand. Let's see what happens. Yeah, this makes sense. It's not pretty, but it makes sense. One last thing, the hip angle cannot be negative. It must be a range from 0 to 180. Same for the shoulder and same for the knee. Just to make sure. Now what I'm doing here, I've created multiple Python files for these. Probably a bad idea. You probably want to stick to one and just build on top of it. But I don't have a lot of experience with software architecture, if I'm being completely honest. And so I prefer to create a new file and, you know, just adapt it as we go. I don't think that was the full code. Please output the full code so that I can execute it, keep my comments. All right, gonna do that. And while that happens, let me bring back the robot to life. Something that I know, I think the voltage monitor died overnight. I forgot to unplug it, and it appears to be broken. It says that it doesn't beep anymore. I don't know what happened to it. Oh, maybe it's back. Oh, it's back. It's very interesting because, I mean, I don't know if I should fully trust it, but it says this cell is unbalanced. It always says they're unbalanced. And I thought these were decent quality lipos. They should not be unbalanced like that. So some cells appear to be discharging faster. Which would be a manufacturing error, most likely. 25. All right, this is a full charge. Oh, is our code ready? Yes. All right, so this will allow us to, we don't have to draw squares anymore. We can just self be a math, and then we can, if anything, we can go back and see kind of like what it looks like. Yep. All right, so starting point, we just define the starting point here. And, something like that. This base is a little short. So we can run this and it'll tell us, and here called angles these angles are not safe, you know, it's because they're negative. The other one's pass, it has a check, which is actually, it's kind of nice. Let me use an emoji here. Check. Okay. So the hip can't go all that way up, right? So we can lower these on the z-axis, the whole square, the whole entire square. All right, so we have 3 checks, and now we have 1 but this knee can't go. It's struggling with the that way the back at the base. I don't know, bring it down more. This seems to work. Let me just sanity check here, just to make sure. So when the hip is 29, and knee is 47, it's fine. The hip 8. Yeah. Hip 24. Alright, this appears to work. I want to break it though, just to see. Yeah, I just want to break it. Just to make sure it's all working. Just to make sure. Oh yeah, here we go. Hip 35. What about 41? I want to see what happens if the hip is like 34 or something like that. $53. Good. Yep, appears to work. All right, so let me go back to the one that's already working here. So this is our square, and just again, just for sanity, this is completely unnecessary, but just sanity check here. Let's draw it out. So 20, starting point 10, and 120, right? So that's our leg, that's our square, and in theory, this should look like this. Like, I mean, yeah, I guess it looks good. All right, do you want to see how it runs in the code? So we had some code, not stand. I know, I don't remember. What did we call our Arduino, IK Arduino here? And then I think we had our positions, define positions. Okay, and basically we just need to copy these from there to here. So 120, 120, 140, 140. So. And in theory, that will do it. So let's try it out. Let's try it out. Too much theory. We gotta try things out. So let's see. Okay, batteries in. I don't even remember. Okay, well, so that's in. You can hardly see it though. Let me see if I can get you a better view. The sun is like not good. Honestly, my setup is like being stretched here. We have like 2 cameras, cables everywhere. Okay, well, what about that here? All right, that's it. That's your view. Now I'm gonna. Oh my god, it's disconnect my mouse. I'll have to come up with a fix for these. I do have a USB hub, but for some reason, I mean, it's like the bandwidth is not enough or something. Every time I connect it, the mouse starts to lag a lot. It's like really annoying. All right. Also, I read that there's a way to push to Arduino from VS Code, and I haven't tried it yet. Haven't tried it because, you know, I think we are gonna move to Raspberry Pi, which you can push from VS Code. So, all right. I would say that looks nothing like. I mean, the good news is that I agree it's like a rectangle. But I think the math must be screwing up somewhere, because I mean the height of that rectangle is just huge. Or did I make a typo? 120, 140. Yeah, this doesn't make any sense to me. The hip should be somewhere between 0 and 29. That makes sense. I think it's always the angles of the knee that kind of like don't make so much sense. Gonna disconnect here for a sec. Bring back my mouse. Let's double check the cat. Let's double check all the math. You know, this might be one of those cases where the math is going wrong somewhere. I suspect that's what's happening. Okay, so let's pick this point here, for example, right? So that will be 50 and 120, and for 50 and 120, the hip should be at 0. That looks about right, and the knee should be at 80 degrees. Let's see, how do you calculate knee angle? Knee angle. So knee angle is that minus 90. So 170 minus 90 is 80 degrees. So that's perfectly accurate. So at least here, things are working out. What about on? Oh God, I disconnected the Arduino from the laptop. Okay, so it looks like the code in Python is working fine, but perhaps it's a Arduino issue. Or did the Arduino math libraries work different? Maybe, I don't know. So let's check that. Your Arduino keeps getting slapped. It's sad. I don't know. I don't see a serial monitor. I think it's because it's already open in a different window here. Let me close some of the Arduino Windows. I guess there was only one. My mouse is disconnected, of course. Okay. So we said that for, we were looking at this one, right? 50 and 120. 50 and 120. The knee is way off here. The knee should be 80, it's getting 184. Alright. Okay, the good news is we found the issue. There's an issue here. I'm gonna pour a cup of coffee to celebrate. I'll be back. All right, let's look at the code. We can turn this off now. I just want my mouse back. That's the main thing. So, all right, let's take a look here. I'm gonna copy this print here. Bring it to VS Code. I just want to compare. So yes, here, and then this is what we should be seeing here. Okay. Oh, this is the Arduino file. Okay, cool. All right. So our knee. Print our knee. Okay, so knee angle. Let's see where knee angles. Okay, yes. Calculate servo angles. I am pretty sure that is the exact same equation we're using here. Calculate linking definition. Wait, it looks like the same thing. For the right side. Okay. I'm gonna have to lose my now. Because like the question now would be, what is link servo theta to, right? So right, so sorry, as my screen, we're running out of screen real space here. But link servo theta 2, I mean link servo theta, link servo beta, link servo lambda, right? So if any of these is incorrect, link servo, like I would have to monitor every single part of what goes into each angle to make sure it's correct. I mean, and that's not impossible. That's okay. Nothing is impossible. Just like thinking of, okay, what's the best way of doing this? I guess here. So just write the name link servo beta and it's a print ln servo beta, right? I think that would work. Okay, and we don't want just beta, we also want theta and lambda. Right? Maybe. All right, and so if we go here, the position we said we're struggling with, I already forgot, was 50 and 120. So we can just make all our positions the same one. So we make sure we're getting the right variables every time. Cool. Okay. Now I'm ready to lose my mouse again. And let's try this again. Uploading. Done uploading. Okay. So now if we go to the serial monitor here, we should be getting data. Yes. Oh, please don't break. All right. So this is basically all we care about. We can go here. Oh. We don't need these anymore. I can disconnect again. I can bring back my mouse. Perfect, very efficient process here. Okay. We can do this in this file, I think. Save to check. Right, so if I put the inputs here, which are 50 and 120, they should return link servo beta. Link servo beta is way off. Way off. Link servo theta is good. And link servo lambda is off. Okay. So theta and lambda are off, but sorry, beta and lambda are off, but theta is good. Beta and lambda are off, theta is good. All right. Okay. taking this back to my Arduino here. Back to like the function where we calculate these things. Link knee, right? Link servo. Sorry, link servo. Okay. So beta and lambda are off. What do these have in common? The ACOS, I guess. And then theta is good. What does theta look like? A10. Very simple. Okay. Let me check the AI. See what the AI thinks. Are these two equations to calculate link servo beta the exact same? Singular link servo. Assuming the inputs, the value of the variables is the same, these two should return the same thing, right? Check. Okay, maybe that's not. I mean, the AI think it's fine. What else is different from this? So theta uses link servo y, link servo x. Beta and lambda use link servo L. Link servo L1. I mean, link servo L1 is a constant, right? Did we mess up the? There's no way to mess up the constants. That's just impossible. I mean, quick check, but it's impossible. Yeah, it's not that. A lot of the times there's like something very simple and silly. You say, oh, you missed a point here. That could be it. But that's how spacecraft can crash also. Unit conversion. Okay, well, what about link servo L? Square root link servo alpha, like servo. Okay, well, why don't we print more things? Let's see if the issue is upstream actually. So I'm gonna lose my mouse again, but okay. So we're gonna print everything. We have theta, beta, lambda. Let's go to alpha and L. So alpha, L. Okay. Just need this part of code. All right, lose my mouse again. Connect to your Arduino. Every time I unplug my mouse, I still try to move it. It's very cool. Thank you, Ryan. Let's use some power. Some poweroni. Some Powerade. Bro, no, don't do that. Okay. That's enough Powerade for now. All right. Back to VS Code, single link. We can basically compare here. Okay, so link servo L is this is off. Link servo alpha off. Wait, these are so off. Are we sure it's the same? Yeah, it's the same. Wow. Oh, wow. I mean, no wonder. Why? Okay, so off. Good. And then servo lambda, we say was off. Okay. I mean, no wonder why this didn't work in. Okay. Basically, nothing is good. I mean, sure, theta is good, but that's because theta is just a product of these two constants we just defined here. Now, what does alpha, L, what do all of these things have in common? I think, first of all, L uses alpha, beta uses L, and lambda also uses L. So if alpha is wrong, they're all going to be wrong. So let's start with alpha. Now, alpha has crank angle, link servo theta, that we said that was fine. So it's down to link knee theta 2 or crank angle. What the hell is crank? Oh, crank angle is a constant. Crank angle is here. So that can't be wrong. So it has to be link theta 2. And so now, you already guessed it, we're gonna print link knee theta 2. And we cannot just, I mean, if we're here, we might as well print everything, like literally everything. So, beta, we're gonna go get the L. Alpha. Theta. All right. So let's see how deep this runs. I didn't even reconnect my mouse this time, so I just thought we're probably gonna need it, or we're probably gonna need the Arduino again. Bro, why? Dude's trying to break himself. Okay, here. Okay. Okay. The knee stuff is here. What matters here? Link knee. Link knee theta 2 is off. Shocker. Lambda here is off. Beta is off. L is off. Alpha is off, and theta is good. Okay. All right. So let's look what goes into each one of these. It's almost lunchtime, by the way. I always film right before lunchtime. It's always like 3 p.m. Getting hungry. I don't know if there's a better way of doing this. I know I always say that. It's like, oh, is there a better way of doing this? That's something I'm constantly thinking about. Is there a better way of doing this? If you know a better way of doing this, let me know. Okie dokie. Okay, alpha. Okay, I have a constant minus bar phi. Oh, that looks like a typo. Okay, now let me guess. Does L use alpha? Yes. Okay. It's a typo, guys. It's a typo. It's always something simple. That is so juicy. Oh my god. Well, before claiming victory, let's compare. If this is actually good now, I deserve lunch. And if it's not, I'm not having lunch today. Very healthy. Knee beta is good now. Good. L. Good. Knee alpha. Good. Theta was good. Knee lambda. Good. Knee theta 2. Good. Link servo L. Good. Link servo alpha. Good. Link servo beta. Good. Link servo theta. Good. Link servo lambda. Good. Oh my god. All right, what did we learn from that? Like, jokes aside, what did we actually learn from that? When you start troubleshooting, maybe start from where you made the last change. In this case, that was the line where I made my last change. So that was 100% my fault. 100% my fault. And it took this long to figure it out. But now we know. Now we know. All right, let's do these squares. So in theory, it should be square. Wait, did I don't know if is this minus 10? I don't remember if this is what we wanted. Minus 10, 120, 50, 120. Yeah. Okay. Let's check the positions that we're printing here. It just doesn't, again, just doesn't look like a square, you know? Which is annoying, but we'll get to the bottom of it. So for 50, 140, we should have hip at 8 and servo at 78, which is correct. I mean, is that what we... No, right? That's not... I don't think that's what that should look like. Yeah, it should look like something like this. Okay, well, okay, let's give it the benefit of the doubt, and instead, let's increase the base here to 120. Sorry, I forgot to save. 20, 0. Yeah. Okay, basically doing trial and error here. I'm just wondering how can we be so off if we're fitting the same angles as onto the servos as there's on CAD, and we know that our servos are properly initialized. How can we possibly be so far off, right? And I think it's mostly on the knee. Yeah, I'm super duper puzzled. Super duper puzzled. All right, perfect. We have another square here that should work. Let's try one more square. I don't know what else could be wrong. I don't know, am I missing something obvious? I mean, at least I guess we're kind of like, we're back to where we started yesterday. Why would the equations look good on the sketch drawing, which has the same dimensions as the real robot, but they don't look good on the robot? Why does that doesn't match? And it appears that we are printing the right stuff. Like, there's like, oh, you could say like, oh, maybe the wiring is off, right? And it's like, well, in that case, the wiring cannot be off for multiple legs, right? So it's like, if I was to start moving the rear right instead, it's like, that shouldn't be an issue. But it still looks very dumb. So what else is wrong? Is our axis coordinates wrong? I don't think so. What else could possibly be wrong? Like, it's a leg with the same dimensions as this sketch drawing, the same kinematics. Is this one of those cases where there's more than one solution to the angles? I don't think so. Yeah, I'm kind of like confused. Okay, let's see. What does ChatGPT thinks off the cuff? Like, I derive the inverse kinematics equations for a robot leg, and it appears to work great on paper and also on 2D CAD. But when I plug it into the robot servos, the robot movements do not match those that the math and the cat forecast. Why could that be? Something like that. Dead zones, not all servos see the exact same as you're feeding them, especially with cheaper ones. No, this is too off. Yeah, I did think about these. I mean, these are all true, just none of them can be that big. I guess they could add up. Height 0. Let's see what happens if we move the height to 0. Sorry, 0. So it should be a straight line on the x-axis. 120, 120, 120. So that should be a straight line on the x-axis, and that doesn't look x at all, right? Servo, no, servos instantly feeding them, especially cheaper ones. Huh. All right, let's do the thing where we just pick one single angle, and I'm gonna measure. This might be the last thing I do before lunch. I'm gonna measure the servo horn angle and the hip angle and compare it to CAD. 120 and 150. Like measure it in real life, I mean. Yeah. 120. Oof, really? Oh, wait, okay. I guess that's actually correct. 150. All right, so our hip should be, hip looks correct. Servo horn is this minus servo knee. $270. Knee servo theta 207 degrees, something like that. But then it's like 270, it's like 62 degrees. So like 30 degrees, roughly. I mean, this position actually does look good. Wait, which servo are we commanding right now? Are you right? thing to notice is that my knee can move without me doing anything. So okay, so it looks like the servo horn might be gone. So we need to fix the servo horn, which is not a big deal. I do have servo horns, replacement servo horns. And I also have a replacement link already. So I'm gonna do that. I'm gonna change the hardware. But let's actually do these on the front, which I think looks very, yeah, the front looks very stable. I did break the rear right. That was my bad. Front. Okay, there we go. So that's what the front thinks that this should look like. Whereas like this is 0. Huh. Yeah, I guess we are deriving the equation for our servo horn here wrong. That explains it. So for the right side, 0 is 90 degrees is here, horizontal. And now we want it here. So this angle minus pi minus 90. Okay, which way is 90 though? Actually, let me check, I guess. So we're gonna do standing, and then front right. We're gonna do sorry, what did we say we were gonna do? Single leg. 177. No, it cannot be 177. Can it be? On the right side? No, this is left. Oh yeah, this is calculating for the left. Okay, front right to here and one to here. Let's try that. Nothing should change. Nothing should change on the front right. Okay, nothing changed. Yeah, this one's broken for sure. So just ignore the rear right for now. We'll fix it. That was my bad. I dropped the robot. I shouldn't drop it. I was trying to show off. Okay, so question. Okay, so if that's 170, what is 90 degrees? That should be 0 full horizontal. Yeah, so for the right side, for the right side knee servos, higher values move the horn counterclockwise. So what would 63 look like? What does cat look like? Yeah. So it looks like we've been calculating that incorrectly. Like our formula is incorrect. Our knee is 270 minus theta. So this angle minus 270. So it's like, it should be 27 minus pi. 90 should be 90 degrees minus 90 degrees minus theta 2 minus 180. Right? So like this. 180 plus 90 is 270. So 270 minus theta 2. That's what we have here. So is that wrong? Well, let's see. 270 minus should mean 62, but it's even 117. Oh, I see the issue here. My man, a lot of software issues from not keeping things up to date. Yeah, 62. Yeah, that's correct. Okay. Oh. What does this mean? Okay, so that's wrong. Oh, I guess it came from here. Okay, well, now let's imagine the other side, right? If on this side going this way is going up, on the other side going this way is gonna be going down, right? So it's still 90 here. So if it's 90 here, sorry, 90 here, shape rotation. It's 27, right? So 90 minus 27. Now we want 90 plus 27. So we want 90 plus theta 2. Yeah, I think so. So that means we want theta 2 minus 90. And then the issue is I have so many different files here that I need to update all of them. Servo knee. So just a little software issue, you know, should be taken care of now. You know, maybe we broke a few things. We broke hardware because of our software issue, but you know, it happens. We learn. Yeah. So I think this is one of the most painful parts of streaming software development, if you can call this software development. We're gonna have this is gonna happen a lot, guys. Okay, so why don't we try something fun? Let's try doing a square again. Of course, wait, actually, where are we doing square? Front right. Okay, front right. Front right's gonna do a square for us. Oh yes. Oh yes. Oh yes. That's a square. That's I mean a rectangle. I'm sorry. That is perfect. That is beautiful. Oh my god. Yes. All right, we're gonna go for lunch now. We made it, guys. It's so exciting. I mean, if you can't tell, like that definitely that matches what we had in CAD. That's so cool. That is so cool. I don't have the thing in drone anymore, but man, that's cool. All right. Gonna eat and then we'll be back. All right. I'm gonna fix some of the hardware parts. So I have replacement parts here, and I'm gonna fix the servo horn that broke. I have a jar full of servo horns. I started printing replacement parts and router filaments, so now we're on the white roll. And this part is half white, half blue, which looks okay. But now things are gonna be white slowly. The whole thing's gonna turn white. I'm gonna time lapse this. You know, you guys don't want to see me like screw things, so here we go. All right, we're back. Robot is fixed now. Everything should work. Everything on software should also work, at least on the right side. So now we can validate the left side, just make sure everything's good. Probably need to consolidate all the different software parts I have, but after that we can just kind of like come up with something that looks roughly close enough to walk in, and sometimes I think my finger is gonna get snapped off because of where the switch is located. Yeah, so I mean this is good. Really, the question here is whether we can do the same thing, but for the left side. Right, so I'm doing squares. I think you can see it very clearly. That's clearly a rectangle. It's perfect. It's very clean. Now, before it didn't work on the rear right. But I am pretty sure it was because of the hardware issue, and if I upload this code now, it should work. Let's check. So the half white leg, rear right is half white, front left is also half white. Oh my god, that was nice. Yeah, looks perfect. All right, cool. The initializing sequence is very rough. We should also initialize to a standing position, I think. Because right now we initialize the shoulders. But we should initialize everything just to standing position to avoid those weird jerks. Anyways, this works cool, right? So now let's do rear left. rear left, rear left. And so now, when we change the boolean to true, so now we should be able to see the same thing happen on the left side. We said rear left, so this one here. Okay. Okay, obviously something went wrong. Okay. So it's math. It's a math issue for sure. Okay, cool. Initialize to standing. Everyone is initialized to standing except this guy. Let me initialize to standing. The issue with not initializing to standing, it's like the servos will harm it themselves. Like they'll, yeah, you see, man, that helps. The right side looks off. Yeah, the issue is this is how we hurt the robot, or the robot hurts itself. That's weird. I thought that was a stance. Yeah, right, because those are equivalent. What's going on here? So 90 versus 20. Yeah, it should be equivalent for the hips at least. Hips should be the same. And then the knee. Oh, the knees are doing something weird. 90, 40. Yeah, it should be roughly the same. I don't understand, man. What if we just do this? I just don't want to hurt any more servo horns, please. That is so weird, man. That is not the same thing. I thought that was the perfect stance. Doesn't seem to work anymore. Did we change these at some point? Did I change these? I don't remember changing these. I shouldn't change these things. History. I know there's a way to see the history and how things changed. I don't remember changing any of these, and I don't know why it's not standing. Let me check GitHub. I know it's technically the same thing, but September. It's been a while. No. $120. I don't think this is gonna change anything. It's still symmetric, and that's not gonna make it look good. I am absolutely puzzled. Nothing changed. What is going on? Front left hip. So the front left should move. Yeah, front left move. I don't understand. Yeah, they should be equivalent, but they're not. This is how we used to get the robot to stand. No, it doesn't do it. I can tell that these are slightly off, but I don't understand why. That is weird, man. That is so weird. I thought this was perfect. Anyways, let's focus on the task at hand. Can't trust stand anymore. And so what we have is this code here that moves things in a rectangle motion, but for the left side, the knee is not quite doing its thing, and it's most likely a math issue here. So if we look at our serial monitor and see what the knee was doing. I know it says rear right, but actually I'm pretty sure, I mean, we can run it again, but I am pretty sure. Can we clear this monitor? Oh yeah, I mean, okay, let's see. I think we just accidentally broke something. Yeah. This popped off. Actually, it might be broken now. Man, that's so annoying. It's because I forgot to switch the function from left to right. It happens. It's just annoying. I mean, my fault. Alright, at least nothing broke. Anyways. We are supposed to write on the left side. So we're supposed to say true here and front left. Oh my god, I hate this Arduino IDE. All right, let's see. Front left. Do a rectangle. It won't do it, but. Alright, you can stop now. Alright. So let's go here. This is what we're getting. This is for the left side, so we can comment things on the right. It's very, yeah, this is a way to get errors, right? I'm commenting things out and putting them on, commenting things on and off to switch, you know, that's recipe for disaster. On the next video, we'll probably just spend time cleaning our software. All right, so the hip is good-ish, goodish. Actually, let's check all variables. Servo, link servo theta 2. Is not here. Link servo lambda 1.3 off. Link servo theta. Link servo theta is 0.6. Good. Beta, link servo beta 1.6 off. Alpha off. Link servo L off. Link servo theta 2, link knee theta 2, 1.4 off, lambda 1.19 off, beta off, knee L off, knee alpha off, knee theta off, right? So I thought we fixed this already. Oh, so this is off? Link me alpha. I don't know if this is right hand side specific. I don't think so. I don't think so. I don't think so. Disconnected. Okay. I have no mouse, by the way, guys. Classic. Yeah, I don't think that's true. So I don't know why this is so off. I mean, what other explanation for link alpha could there be? Burial phi. Okay, well, basically I think we need to print even more parameters from the Arduino. Let's get phi. Variable phi, and let's get g, and let's get variable theta. Kind of annoying that this is happening again. It might just be something, I mean, yeah, it's probably something very simple. Just, oh, forgot to switch something for the left side. Okay. here we have it. I'm basically just using the Arduino to compile C and get results that way. G 192 phi is, oh okay, so even the IK stuff is out. Why would IK be off? For the left side? That doesn't matter. I must have missed something huge here. Does it actually matter? I mean, wait. Okay, so alpha phi is 1 0.98 times 180 by 14 56. So here their phi is 80, basically 89, and our phi here is 56. No. We're getting so close. I have a hard stop in 20 minutes. Man, we're getting so close. Let's set ChatGPT off the cuff. When doing inverse kinematics for a quadruped robot leg, do I have to change my equations for the left and right side, or do they use the same? Let's see what it says. ChatGPT, you know. Okay, flip the they want us to flip. Actually, wait, first of all, why am I even comparing it with these guys? These should match. If something's wrong in the equations, it will be wrong on both. They should be using the same logic. Like, they could both be wrong, but they should both be equally wrong. They should have the same stuff. So bar phi. It makes no sense that they're not agreeing. Man, I'm tired of debugging things here. The fact that phi is already off here, it's kind of weird. I don't get it. Okay, let's add more. Let's add more print statements. When in doubt, print more. Oh my god, oh man! I swear we have probably run into every single possible issue here. omega, but it's okay. This will be our advantage. Oh well. Variable D is off. How is that even possible? No. I know something's wrong here. Alright, something's 100% wrong. I probably didn't save for something. Let me run this again. Oh yeah, now it matches. 120, it's good. G is good. Okay, now yeah, I totally forgot to save. Yeah, now it's good. Theta. Okay. I was gonna say it's impossible for these things to not match. Link me theta 0. Sorry for the drama. Alpha. Yeah, in VS Code, basically, if you run the script before saving it, it will run the previous version. And you can have autosave enabled for that. Apparently I don't. Maybe I should. Lambda 0, theta 2, 9.2, servo L, 37, perfect. Alpha, yeah, beta. 1. Beta, yeah, theta, yeah. 0.61 lambda. Oh, everything's perfect. Okay, cool. So everything is working the way it should be working. Now it's a matter of math. So we said, I don't know if, okay, for the rights, yes. Okay, so here, so I'm gonna say system nodes, and then for the right side knee servos, okay, that implies that for the left side knee servos, higher values move the horn counterclockwise, right? So let's see how the code changes. Oh, there's no clean way to do this, man. Okay, so right now, you know, the left knee is 80 degrees, which means it's moving counterclockwise, and then the right knee is 99 degrees, moving counterclockwise. That makes sense. Okay. Okay. Now our drawing, I think this applies to left or right. The difference is the angle, where we measure the angle from, right? So we said that 90 is horizontal, and for the left more means moving clockwise. So more would go this way, but it's less right now, so it's moving this way, and it's 99 degrees, so somewhere here. Let me see what it looks like on the Arduino, and yes, this is gonna hurt the hardware a little bit. Front left shoulder, front left. This is gonna a little iffy, but okay. Wow. The servo is so strong, the whole body flexes when it clashes. It's actually really cool to see. These servos are probably too strong. 150, 50, 120 here, 80. Degrees. Wait, so it's 80 degrees at 50 and 120. So 50, no, 120 and 50. It's 80 degrees. So that makes sense. Yeah, that makes sense to me. Why is it? If I look confused right now, it's because I'm very confused. Yeah. Let's look at the way we calculate this. Okay, so it's like, if it's the left side, then it's gonna be theta 2, which is this, minus 90 degrees, which is basically this angle here. And so this angle increases, goes clockwise. That makes sense. That's actually perfect. Okay, so what else could be wrong? The angles we're calculating look correct, right? So 50 and 40, hip is 171, which is 171, and then the knee is 78. Kind of close enough. How we're calculating the hip. The hip is bar theta plus 90 degrees, right? So 89 plus 90, 179, yeah. Before it was 90, yeah, that makes sense. Yeah, also makes sense. Okay. What else? What else does it make sense? Or I don't get it. Should our angles be different if it's left or right? Like, should this be a different sign? No. Right? I don't think so. I'm so confused. This should work. This should work. This should absolutely work. Okay, let's just try manually setting the front left hip to 179 and 80, and so these should match in theory. I think should match our cat here. Nothing changed. Is that a typo somewhere? Oh my god. In the Arduino IDE, you don't have to save to upload. Okay. No. All right. So what if instead... Wait, was it? Yeah. What is instead is 110? Does that look like cat? For it to be 110, we would have to be measuring from here. Sorry, that would be 100, not 110. In no universe you can be at 110. Did it even change? I didn't notice. Okay, so it's between that or these, or 80. So the angle came down and it moved. The angle came down and it moved clockwise. The angle came down and it moved clockwise. So this is incorrect. So let's just check, right? So if we go to 90, so higher value, it's gonna move clockwise. Barely saw it move, to be honest. Okay, higher value means feels like higher value means counterclockwise, which is the same one as on the other side. Yep. How can that be? It's like, that makes no sense. So should we just give them the same angle then? It should not. This should not be the case, but that's what I'm observing. So, I mean, I'm just gonna act on my observation, and I might wreck the servo. I do gotta go soon also. But this is so interesting, I might come back later. Can't sleep without cracking these, you know. There is no way this cannot work. This makes no sense. Yeah, it's wrong. Okay, so let's see what 90 is for this front left. I mean, it's just so off. That shouldn't be 90. I must have initialized it wrong then. Let's see 90 on the right, on the rear left knee. How is that 90 degrees? Are these guys high? That is, how can that? What? Don't get it. I do not get it. On the other side, let's look at 90 on the right side. And what is going on here? 90 should be the servo horn perfectly horizontal. Like that. Exactly like that. Okay, so my only conclusion from this is that the left servo horns have been initialized incorrectly and we need to change it. So I'm gonna print new horns and do that right now.
Tomorrow.
Alright, hello guys. So I fixed the hardware the other day, and then that was Thursday night. Then on Friday I didn't do anything. I was writing my YC application, which I will probably do a separate video about it. I'm gonna submit it today, but in order to submit this, I need a demo of the dog walking, just to prove that it actually works. And also, like, I've been trying for way too long to make it walk. We've run into all kinds of issues, right? First we had math issues, then we had programming issues, then we had servo initializing issues. Recently, the other night, I found some mechanical issues that I actually didn't put on the video, but when you put too much weight on the leg, the knee joint pops. So we gotta redesign that. It's like it's too shallow basically, but yeah, I gotta fix that. The only thing we haven't run into are electrical issues, and I'm very, very thankful for that. I'm gonna put a fresh battery in here, but yeah, I am pretty sure that now everything should be working, and so the plan is in the next hour make this walk, then record a video for YC and apply, and then eventually I have to edit this because we've been recording for so long. I need to edit that. That'll take some time. Eventually upload that to YouTube. The one thing I would say is that as I am filling the YC application, part of me is like, wait, do I actually need YC? And that just might be me being very optimistic, but I'm like, could probably bootstrap this. Could probably bootstrap this no problem. If you make some assumptions of how much engagement you can get from making robots. Alright, that's that. Now I need to connect this to the computer. I hate wires. Have I said that before? Freaking hate wires. here are getting out of hand now that everything's broken. The other thing I need to make is a little roof, like a little plate to put on top to cover the top of the robot, so the wires are not like spilling out everywhere. We'll just enclose that. Let me disconnect my mouse and all this stuff. Oh. But yeah, so where we were last time was that the left legs were not matching the right legs, even when we mirrored the servo positions. So that was really odd. And we trace it back to being an issue with how we initialize the servos, which is really odd actually, because I don't know how I would mess that up. I think that, like, we had the process down, but let's give you a better frame. These be the robots. You're looking at the right side. And so now, you know, if we go here and we do the standing function here, and we upload this to Arduino and like upload it, just upload that, all the limbs move like it's symmetric basically. All the limbs move the right way, right? So you can see here, you know, it actually looks like it's actually standing, right? Like look, it looks like it's standing. Now if you put it down, the weight, you see, look at the right knee there, it wants to go. I've taped it together for now, but that joint needs to be beefed up. But like I said, I just need a video that kind of looks like it's working for YC. So look, it's standing, right? And it's like, now standing isn't hard, of course. We knew how to stand. We've known how to stand for a while. I just need this leg to not explode, please. Anyways, now that the servos are all behaving, we can go back to what we're doing before, which was walking. So we had this walking function here, so I'll just upload it. Kind of like don't remember exactly what we had here. Remember, it's doing squares. Pretty straightforward. Sorry, I'm trying to get the other limbs to just stand. Yeah, so they should know what they're doing right now. Yeah. Yeah, and so in theory, this is highly theoretical, but we could say we could do the same thing for the left side. So this is front right, so we can do front left here. Again, highly theoretical, but why not? And so now on the left, it should work. Oh, sorry, I forgot to comment this out. It should work. Wait, okay, maybe I forgot to change some logic here. Servo. I think we changed the logic for the left knee. right? So it's like I don't remember what the right side looked like doing the same thing. Sorry. Alright, so this is what it looks like on the left side, right? And then on the right side it should look like the same thing. And it does. Looks like the same thing, right? So that's cool. All right. By the way, I don't know why the other legs are doing this like thing. I'm gonna just tell it to stand for now. So let's take a quick look here at the code. Why are the legs doing this thing? I think when we call, no, actually setup delay. Yeah. I don't know why it's doing this. I think we don't need that. Let's try. I think we don't need that. Yeah, there you go. Cool. So fix that. I'm still gonna put standing just because like when the right leg moves, it keeps hitting the Arduino cable. Anyways, all right. So now that we can move the legs accurately, finally, really all we need to do is to make it walk by moving, legs. Kind of like just I actually I know this has been very contested. How do you walk? Like diagonally, you crawl. Crawling seems to be the easiest one right now. Before we talked about how the robot's not stable on 3 legs. And now the rear right knee wants to like explode. So we're not gonna try anything crazy. We're gonna crawl. It's gonna be very safe. And so I don't know, like we can Google quadruped crawl. And okay, it's funny that you Google these and it's like people crawling. But yeah, it's like a baby crawling. But that doesn't really help. Quadruped robot crawl. See, and the spiders don't help either. A fast crawl gait. Oh, that's interesting. This robot looks very nice, actually. A lot of people have built very nice robots. It's like, that's cool. All right, let's pay attention. So the rear right leg just went forward. My brain's feeling smooth right now. What's the logic sequence for a quadruped robot crawling gait? Let's see what ChatGPT says to that. For a quadruped robot crawl gait, you want slow, stable, low speed. Yes, these are all the right words. Solutions. Aim for a 3-1 leg support phase. Exactly. Yes. Leg lift sequence. Start with 1 leg. Then shift the weight to that leg. See, that part we can't do. We haven't coded body rotation yet. Body roll. That's we have a lot of work to be done on the software side. After front leg plants, lift and swing the rear right leg. Continue the diagonal pattern. Okay. What is the motion of the leg? Is it a rectangle? Can we break it down to 4 points? Rectangle corner. The motion of the leg as a crow can be thought as a roughly rectangular if you're looking at it from a top-down view. No. What about a fully ground support? Okay. Leg pushes forward while ground until it reaches the front. Yes. Leg lifts from the ground and begins. Leg pushes forward while the ground. Wait, leg is at the back of a cycle, fully grounded, supporting the robot's weight. Leg pushes forward while grounded until it reaches the front. You sure? Left legs from the ground. No. What about if we look at it from this side? I don't think ChatGPT is good for these things, actually. What about trapezoidal or slightly arched path? Point A, start stance. The leg starts on the ground at the rear. This is the beginning of the stance. Yes, okay. The move forward while still grounded, reaching its maximum forward position. This is... No, why would you move forward while still grounded? This is the end. I don't think that's right. Yeah, see, if I had to break this down, there's like grounded at the back, then you start lifting, and then you're grounded at the front, then you push on the ground. So maybe it's not a rectangle, it's actually a trapezoid. It's a triangle. I think we can do rectangle though. See, even if we achieve this today, I'll be happy. Anyways, I think we're on something here with our rectangles. So this is the function we wrote to write rectangles. I just want to make sure that our math is still correct here, because I think we changed some of the math, but it's kind of like we probably didn't update all of the files, right? So this is knee, the knees, servo knee, right. So the right knee 270, yes. The left knee, yes. Okay, let's triple check here the hip. Where is the hip? Here's the hip. Just triple checking. I don't want any more errors, especially if they're avoidable, please. Hip 90, yes. Okay, hip 90 minus, yes, perfect. All right. Okay, so now let's look at our let's just look at our current rectangle and like take a guess if it looks correct. And if it looks correct, we'll go ahead and, okay, probably doesn't look correct, right? I think the leg is too flexed, too up. So we can go here and change the starting point on set. We want to increase set here, so we can do like 170. Also, I think it's too backwards here, so we can do like -20 or something like that. And then we can run this script. And I know this process is very artisanal, very manual. Okay, so now we have these new points, and so we go here. Or I guess we can go straight to the Arduino IDE, which I hate, but it's okay. -20, 80, 20, and then it's 70, 170, 170. Oh, I know what's wrong here. I made the base 0. Base cannot be 0. Base of 20 is probably fine. We'll start again here, minus 20, 70, 90, 90. Okay. So let's try that and see if that looks better. I mean, to be fair, the standing position did get a lot better. The starting point is a lot better. If you want to try minus 30. We're probably swinging back too much, so I'm gonna reduce the base here to 60 and increase the height a little bit. Let's run these. Okay, passes a safety check. Remember, the safety check is checks to make sure none of the servos are gonna clash, because we haven't written that in code yet. All right, let's check that. I think that looks great. I think that looks really good. So if we were to compare that to this guy, okay, maybe we can increase the height a little bit, just a little bit. I'm just nitpicking here. So height, we'll go to 50. Cool, this passes all the checks here, 30, 30, 30. All right. Let's see. Okay. So now, what's wrong here? The sequence is wrong, right? I think technically we should be starting even further up. Like, it looks good, but that's where the leg starts, back there. I think that's too far back. Is it? Let's see if we can push it a little forward. The starting point here, maybe like 60. I don't know. I'm just trying things, see how they look, really. Let's see. Okay, I think that looks even better. Now, one thing to keep in mind is the sequence at which how we're executing things is wrong right now, right? So first, we should be starting from here. And I'll explain if it's not entirely clear, but so from the back, right, all the way back, then we're gonna lift our feet. Then we're gonna push forward. And at the very end, we're gonna bring it down. Like, that's the correct order. And of course, it won't look different just because it's a loop. But the other thing is, let me speed this up. Let's see what happens if we go faster. Let's turn some lights on. Looks like we can go even faster, right? I'm just eyeing it out manually. You want to make sure, basically, delays give enough time for the servos to go where they have to go. Oh, I just realized, wait. We're segmenting wrong through these. It's going backwards. It's basically walking backwards, I think. Yeah, I'm pretty sure it's walking backwards right now. So let's fix it. Yeah, I think something like that is correct. Go even faster. Okay. Just for science, faster. No delay. I wonder if this is the limit of the servos. I'm gonna bring back a delay here, just to be safe. But oh no, oh no, oh that was my bad. That was my bad. Sorry. Did you see what the shoulder did there? Let me see these parameter effects. We want to start at the back, I think. Oh! I don't know why the shoulder would do that. Okay, anyways. Okay. Okay, so now we have one leg moving at a time, right? What do we actually need to crawl? We need all legs moving at the same time. I wanna check this coding. Okay, so let's look at how this guy does it. Just like, by the way, look at what he has in the background. He says simulator running. We don't have that. Actually, it would probably be nice to run this in simulation. I didn't think of that. Okay, so it looks like the next leg starts moving up before the first leg starts pushing backwards. I see. Okay, let's ask the AI for some help here. Describe what this code does. I like to have it describe what the code does, just to make sure I can see it understands it, and also adds context to the context window. Look at the beautiful kinematic expression. Okay, boy. All right, so right now we are moving one leg in the loop, but obviously for the quadruped to move forward, we must move all 4 legs. The way I want to do this is through a crawling motion. One leg will move at a time, 3 legs will always be on the ground. Now, one leg should cycle through positions 1 to 3, and the next leg should start cycling through positions 1 to 3. The first leg should only move to position 4 once the second leg is in position 2. We will do these diagonally. So first the front left leg will go, then rear right, then rear front, then rear left. Can you help make the modifications to the code? Okay, I'm sorry for the bad language of my AI. Maybe I should tweak it, let me open a new file here. I'm gonna okay Arduino single. I'm gonna copy this here because yeah, for single leg I think it works good. I want to keep that maybe in the future. All right, let's see what it's proposing. So leg state, grounded, moving. Okay, so introduce a new global variable here called leg state. Okay, each leg has a servo shoulder, a hip, and a knee. So 3 servos. It has a current position. It has a leg state, so grounded or moving, and it's either left or right. And then here it calls the legs. That's neat. I like that. Fully grounded. Okay, they all start in grounded. And current position 0. Okay. What else? Okay. It removes some empty spaces. Okay. It's removing current position 1 because it's part of the leg variable now. Okay, and it's removing all of these, all our print statements. All right, let's try it. I mean, I think it looks correct. It might just need a little tweaking, but let's try it. Legs was not declared in the scope. Oh, wait, what? I'm gonna pass the error while I look at it. Next leg. That's odd. So let's see where Lex is declared. So it looks like Lex is not declared anywhere. Let's see what it says. Declare the Lex array. Okay. So I forgot to declare the Lex array. Let's see. It's basically this line here. And this change here. All right, accept the changes and run it. It moved the first leg, but it got stuck on the second. And we can say, so the first leg moved front left 3 positions, but then nothing happened on the rear right leg. Why could that be? We're not seeing movement because servos are being commanded to correct standing starting position. I don't think that's the issue. But it did add some serial debugging, which could be helpful. So let's see the changes. Okay. Okay, so I guess the stuff that I commented out had some purpose. Let's accept that, and I don't think it implemented the zero monitor stuff. So I'm gonna manually implement this here, like that, and let's go here and upload. Whoop. What's wrong? Positions was not declared in the scope. Pass that stuff. I think that has to do with the new position stuff here. So it doesn't know what positions is, because positions is declared, or is positions. Define positions already, so it's down here. So basically just needs to move things around a little bit. It's not a big, yeah, literally move it up, move those lines up. I could do it, but we're gonna have the AI do it. You can't take credit for everything, you know. All right. Let's see if it did what I thought it was gonna do. Okay, so you moved it all the way up here. So it's now a global variable. Move this also up. Okay. I think that looks correct. So let's try to run it. And now it should work. Whoa, yes. No, quite. And look at the serial monitor. I mean, everything moved once, and that was it, right? So first of all, I'm gonna simplify this. I'm gonna clean the serial monitor here. We don't need this stuff here. This was for troubleshooting math and linkage stuff, which it's working now. So just remove it. And that will clean our serial monitor a little bit. And then let's run it again. Looks like we lost connection. Zero start, zero begin 9000. That's kind of odd. I mean, we're always connected. It says uploading. Delete this. I don't know what's going on. All right, so let's walk through the loop here. Can you help me understand what's happening in the void loop? Let me break this down. Okay. I don't know what being called an absolute sigma means. Okay, so static active 0 cycles through. It's basically invented a walking gait where each leg moves through 4 positions sequentially, like a high frequency training order, but for this code won't let a leg complete cycle into the next inspection to lift and ready. Will the robot keep walking in an endless loop? Okay, but right now the robot is not walking in an endless loop. Basically, current haven't as current length. The issue is in checking for current length equals current position. Once the leg reaches position 8, only move position 4 compensate if the next leg is in position 2. In this condition, is met your robot stacks like a shitcoin after a rack pull. Here's very neat. Diamond hands. This manipulation ensures continuous movement like compound interest. Okay. Explain to me like I'm 5. What changed? So, whoa. No. That's not correct. Listen, I'm kidding right now. It gets stuck. The old code distance waiting for next to it, but what's next? It's not moving because my new code when stuck make your next evil. It's like pushing a person through. Let's see. All right, so this is what actually changed. Empty space. Current like okay. Listen, let's just try it. I'm not even sure if our positions are. Oh, okay. Well, sorry. Okay, we obviously need a delay here, higher delay. Interesting that you can move that fast, but okay. A little faster. All right, so it looks like. Well, actually, let's just take a look here. But would that work? Yeah, so I think it looks good, except the position numbers are incorrect. So what's position 0 should not be 0 and so on. So I think those are defined. There should be an array, or what do you call this? This is, let's see. Is this an array, library, or what? I just want to make sure I'm listening to the array. To the array. Okay, cool. Okay. So position 1. This is back and grounded. This is back and lifted. This is front and lifted, and this is front and grounded. So gonna keep this here. Can you explain to me in what order do we cycle leg positions? Let's see what it says to that. All right, each leg moves to 4 positions. Back and grounded. Okay, it's a diagonal gait. Very elegant. Let me break this down. Okay. Do the legs do the diagonal leg weights for the first leg to reach position 3 before moving to position 2? Weights position front and lifted. Back and grounded, back and lifted, front and lifted. What is the natural position for the non-active legs? I think that's what's wrong. Then it's 1. Okay, so legs are in 1, back and grounded. Oh, I got it wrong. Or is grounded. So how do you know if a leg is ground? Oh, no, never mind. Okay, so back end lifted, back end grounded, back end lifted. Okay. Can you verify the order sequence is indeed correct? So I had lifted and grounded upside down here. Remember that when this number is higher on the Z axis, the way we define Z axis, it's closer to the hip, right? So it's distance from the hip pivot point, from the shoulder, from the hip pivot point actually. So the smaller the number, the shorter the distance means the leg is off the ground. Wait a second, let me fix those comments. No, the comments are correct. Yes. Oh god, you're right. I need to. Is the walking sequence is still correct, or do we need to rearrange stuff? Yeah, we need to start grounded. All right, so we should have this here. So this will become position 2. So we start grounded, then we lift, then we go front lifted, and then we ground again. I think so. Let's try this. How does this look? I'm gonna ask the AI, but also I'm just gonna run it because I'm gonna also increase the delay because I think we're using a lot of energy for no reason. All right, let's check that out. Okay, the grounding position looks much better. I am tempted to put this on the ground. I want to move this to the rock, the carpet. More traction. Also, what did the AI say? Let's see, just to make sure it didn't make a good point. So it cycled it to 0, 0, 270, 270, 170, which is exactly what I did manually. So that's good confirmation. All right. Are we in frame? All right. Why are we not moving forward? Okay, I see the issue. So we're cycling the legs, but we're never pushing the ground in order to move forward. We're kind of like walking in place. So it should be a quick fix here. Okay, great. I tried this, but the robot doesn't move forward. It appears that the issue is that we are moving the legs in the air, but we never actually push the ground back to move forward. Also, it looks like the rear leg is broken. It popped off, which is what I was talking about earlier. No. Alright. Oh. Okay. See, the switch is fully in the way of the leg now, so to turn it off, I need to raise my finger. It's a bad design. only happens on this leg. I don't know why. They're all the same geometry. So we have that, and on top of that I'm going to tape it. And hopefully that will hold. You're absolutely right. This is like going to okay, for the robot to move forward we need to ground it like to push backwards positive x while the other legs are in this cycle. Okay, so it does understand. Right now we need can you output full code to do this? All right, let's do that. So we're adding a fifth step. I actually don't believe that's a good idea, but full code, please. How do I implement? Oh, yeah, 2 positions actually. Interesting. And we can try it. I don't know why I'm not getting the Thunderbolt. All right, so let's just do it manually here. The whole reason why I used double was to not do this manually, but void update. Does this even exist? I'm gonna start a fresh conversation. I realize that this walking gait never pushes back on the ground to actually move forward. How can we fix this? Okay, so 5th position. I mean, I don't think this is correct because going from 4 to 1, so wouldn't going from position 4 to position 1 be the equivalent of pushing backwards to move forward? but we never actually. Do we actually go from 4 to 1 in the current code? Visually, it doesn't look like it. Let me make it move even slower, just to make sure, but I don't think so. Also, I added 2 new positions that, no, I didn't. Sorry, I messed up the annotation here. Yeah, if you look at the robot, it never goes from 4 to 1. In this walk-in gait, do we ever go from position 4 to 1? We need to explicitly go from 4 to 1 so that we can push the ground back and move forward. Okay. Let's see what it's proposing here. And then we can try it to walk again. Hopefully the knee doesn't explode. No. Reject. Don't get rid of that. I'm gonna accept. Didn't fully grasp that last change, but let's see. Oh, so you got rid of some logic. Wait, this is good because now we go from 4 to 1, but you got rid of the logic where the second leg only moves. Whoop. When the first leg is on the air, position 2. Okay. Let's try it. So we should start on the front left leg. Honestly, it's kind of hard to not do if it works or not. Another leg popped. Alright, so these knees are very fragile. Just like we're learning these now. Alright, so knees will have to get redesigned, but not today, there's no time for that. We could just tape all the knees. Can I get scissors? shoulders a little bit to see if we can gain some stability until we fix the knees for good. I think technically that was walking, but you know, if I'm holding it, helping it with my hands, then I could see how it doesn't count. Oh, I see. So my shoulder flare is not working. Okay, maybe now. I see no shoulder flare. Did I? I'm going for exaggerated just to make sure it's working. No, I don't see it. I'm gonna comment this part here. I think these might be overriding my flares here, but we'll see. And yeah, the camera's pretty far, can't really see here. I flared the left incorrectly. Left side, left side. Alright, so you see here now, basically the shoulders are angled outwards, so in theory, I think that will make things easier on the knees. The knee failed there again, but despite the tape. Alright, pretty lame that it's a mechanical issue. Yeah, immediately it fails. Yeah, I don't think I can fix this. It will take hours. And I seriously need to put the switch somewhere else. Turning the robot on and off is seriously. Okay, so reduce the flare. I don't know what else I can do. Make it go faster. I think that'll put more stress on the knees. I think technically this is walking. It's just We could also remove some of that weight somehow. Okay. I think I'm gonna call that to be walking. Technically, I think software-wise, we got it to a place where it's walking, but we're gonna have to. We need stronger knees, basically, and that's gonna take. Well, first we need to cut that, and then we need to print that. But that'll be too long for the YC application. So instead, for YC, I will animate something standing. We'll pretend that this was walking for the video purposes, and then next video we'll make better knees. We'll put a cap to hide all the wires, and we'll keep working on the software. Probably body inverse kinematics for roll and yaw. But I think this is a good place. So I'm gonna end it here.